Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, and we are hitting section 4.8 in the Big Ideas Math Integrated Math 2 textbook on solving systems of non-linear equations. Now, if you've taken an IM1 course, you've probably done systems of linear equations, where you find where two lines intersect, you find the x and y. If you solve by graphing, you can also solve it algebraically using something called the substitution method, or the elimination method, and either are very applicable in how we go about in doing them. And we can use that here. We're going to be doing the same thing with nonlinear equations. By this, we kind of probably mean more quadratic equations, or at least one equation's quadratic, maybe the other one's linear. And I think through a preview of some of the problems I've seen before, because I started to teach this to my students already when I covered this, so I haven't really seen the problems in the book in great detail, but that's what I've seen, kind of one quadratic, one linear, and that's the extent that we will do visually. So we're going to find where two lines, where a curve intersects with a line more likely, and it can be more than one point. So we're going to find those points of intersection. That's going to be that big overall goal. And then we'll also do it algebraically. We'll find those solutions there using practical means. A lot of them, because they're like, we want to actually find those points, they're probably going to be integer values. So not only rational solutions, not only real solutions, but also rational solutions, and also probably integers, which is pretty nice, which means we can solve a lot of these by factoring, or some simple square roots or something like that. So let's take a look at the, the lecture portion of this and see everything that they're going to cover. We are going to solve systems of nonlinear equations by graphing. We're going to do it algebraically. And that's right, I did see this. We're going to approximate solutions with equations. So get your calculator ready for those, or at least follow along with what I have. That's something that can make this video probably go longer than it has any need to be. So I got to do things in the calculator, typing in equations. We got to find where things go in a table. Let's see how they go about it when it comes to approximating. We'll do our best. Okay, and we're also doing graphing. So get your graph paper ready. I'm going to attach in the PDF section down below this graph paper along with timestamps, and check out the playlist and all that kind of stuff. So systems of nonlinear equations is our core vocabulary. Systems of linear equations would have been something previously learned at some point. And let's take a look. The methods for solving systems of linear equations can be used to solve systems of nonlinear equations. So whatever we did here, we can do here. A system of nonlinear equations is a system when at least one of the equations is nonlinear. Like I said, you'll probably see mostly quadratic. We'll see if we run into anything else, but if we do, it'll probably be in the approximation stage, not in graphing them or something else like a cubic. When a nonlinear system consists of a linear equation and a quadratic equation, the graphs can intersect in 0, 1, or 2 points. So the system can have 0, 1, or 2 solutions as shown. Now, if you go to section 4.2, guys, we did solve by graphing, and we did something a lot like this, particularly using that method number 2. It was a different setup for 2 reasons. Number 1, it was a single equation, and we treated them like y equals this side and y equals that side, which is exactly what we're going to do here. Y equals this, y equals that, and just graph them. Number 2, we only found the x values at the time. Here we are now going to find what specific x or x's give me the same y for both, and what are those y's as well. So that's the difference here, is that we are going to use that second method version each time, graph one, graph the other. And then we're going to find the xy ordered pairs where they intersect, not just the x's, but both, or if they don't intersect at all. Okay, so solving by graphing. Let's solve this by graphing. We have 2x squared plus 5x minus 1 and y equals x minus 3. For the 2x squared plus 5x minus 1, let's see how they say graph each equation. At this stage, we've done chapter 3 where we've done a lot of graphing. 4.2 we had it. How do you graph this? Negative b over 2a is where you can get a vertex. Here's a y-intercept and find its corresponding point. A lot of things you can do to get the actual graph itself, which I'm not going to teach. I'm just going to do. But, you graph this thing, here's that parabola right there. And y equals x minus 3 is slope-intercept form, y-intercept of negative 3 and a slope of 1. We graph that. They only intersect at one spot, and we're going to have to be really good at our graphs to make sure that we understand it only hit one spot. What is the ordered pair? Negative 1 for x, negative 4 for y, negative 1 comma negative 4. That's where they intersect, therefore it's the solution. They're double checking that as well by substituting negative 1 in for x into one equation, and they get negative 4 for y out. They plug negative 1 to the other equation, they get negative 4 for y out. This is an important stage where we solve algebraically, not by double checking, but by showing how you get the y value when you find an x, and showing that you can substitute into either equation for it to work. So unless they force me to do it for either equation, I probably do it for the first couple, and after that I'm probably not going to do it there on out. But that double check is just to show you that, hey, that is the correct number, especially when we do graphing. Things can approximate. You're going to have to be careful. So we might have to do that every so often. Here are a few more to solve by graphing. We'll wait for the problem set. Okay, solving algebraically. We have two different methods that we can solve using. Number one is via substitution. The substitution method is a version of taking an expression on one side and setting it equal to an expression on the other side, like this, y equals. And if this can go ahead and replace the y in the other equation, x squared plus x minus 1 can take y's place over here. So you have an equation that has no y's and all x's. The end goal is to be able to solve for one variable at a time. So these equations are solved for with y, meaning y is by itself. You can substitute x squared plus x minus 1, or, okay, they did it the other way. You can substitute negative 2x plus 3 in for y in this other equation. Now, why can we do this? Because y equals negative 2x plus 3. So instead of having y, write negative 2x plus 3. So boom. And at this stage, I mean, ignore anything else that says system this or that. When it comes to solving for x, I say solve for x here. Do it using any quadratic means that you prefer. I prefer setting it equal to 0 and solve by factoring, and it looks like that this is what the book does as well. Add 2x over, subtract 3 over, boom, set it equal to 0, solve by factoring, 0 product property, you got negative 4 and 1 as your two values. But you're not done there. We then, just like graphing, we find the y value that goes with these. Now in the previous problem, we only had one point of intersection, so there was one ordered pair, negative 1, negative 4. In this one, you can see there are two different x values that we have. These are two different, here's a graph that they made. There are two different ordered pairs where these two graphs intersect, at negative 4 comma something and at 1 comma something. And we're going to find those two by substituting negative 4 into one of your equations. It doesn't matter which, you just saw in the previous problem. You can do it in either, you'll get the same way. I plug in negative 4. Now, which one should you plug it into? I would do, and they're going to do it too, I would use this bottom one. There's no quadratic. There aren't two different places to plug in for x. Less chance of making a mistake. Plug negative 4 into here, plug 1 into here. However, if you substitute negative 4 into here, you should get the same y out, which is 11. And if you plug 1 into either one, you should get 1 out. So negative 4 comma 11 is an ordered pair, and 1 comma 1 is an ordered pair. And make sure you distinguish the two. X is negative 4, x is 1, y is 11, y is 1. Make sure you don't put negative 4 comma 1 and 1 comma 11. They have to be specific to the one that you plug in. So if you plug negative 4 in, you get 11, that's an ordered pair. You plug 1 in, you get 1, that's an ordered pair. Two solutions to this. Here's the graphing version of it. Not that you'd have to do it, this is just a visual representation of that. So solving by substitution is pretty straightforward. We'll do more together, but it's really nice when y's are already by themselves, and it doesn't need to be both. You just need some variable by itself, so you can then substitute this in for the variable in the other part, wherever it is in the equation. It's recommended for all of these methods, though, you just get the y's by themselves. It's just natural when you do graphing. And for the elimination method, looks like they're going to do that as well. I just took a peek at this. Solving nonlinear systems by elimination. Now, the elimination method is something in IM1 that you are probably used to more doing for something. I'm just going to make something up. Like 2x plus 3y equals 6, and then x minus 4y equals 12, something like this. And you'd be in standard form of a linear equation where x and y were on the same side of the equation. And then you'd say, hey, let's multiply this thing by 2, and then, minus 8y equals 24. I'm reminding you what it looks like. And then you can add, let's do negative 2. 2x times negative 2 and times negative 2. You get negative 2x plus 8y equals negative 24. And then you use that to eliminate these x's. 2x minus 2x, boom, is 0. They eliminate. 3y plus 8y is 11y, like whatever, that kind of thing. Equals, this would not be a good example of a problem because you can't, that's terrible. This is what that elimination method looks like. Hopefully that rings a bell. If not, you can find some videos of mine where I do that kind of thing. However, on these problems, because they're generally quadratic, or one of them is quadratic, then your result by adding down the list will also likely be quadratic. That's the goal of what we're doing in all of chapters 2, 3, and 4, dealing with quadratic equations. That being said, most quadratics, just like this last problem that we solved, it's good to set equal to 0. So having y equals on these sides of the equations is probably pretty good for us. Don't put x's on the same side with y. There are multiple degrees of x, and just getting it equal to 0 by eliminating y is our goal. Because the coefficients of the y terms are the same, 1y equals 1y equals, you do not need to multiply either equation by a constant. The only value I would recommend you maybe multiply by is -1. If you need the version that says let's change all these signs, that's something I'd probably recommend that you do. You're probably going to see me do that, which means change all the signs and treat the signs as they are. That way you see y minus y is 0. And then x squared doesn't combine with anything, but -3x plus 3x is 0, and -2 plus 8 is 6. So you'll see 0 equals x squared plus 6. Let's look down below. 0 equals x squared plus 6. What they do is they subtract, though. They subtract. Just be careful if you do subtraction, meaning negative minus a negative is addition, right? So I'm probably going to change the signs. Negative, plus, plus, like that. Make it a little easier for us. Sound good? Sound good. It's all for x. This one is best to solve using square roots. We subtract 6 over, and then we take the square root of both sides. But you can tell we can't take the square root of a negative. Now, that being said, we were just doing a lot of square roots and negatives. Here, in the past, we'd say x equals plus or minus I root 6. By in the past, I mean last section, section 4.7. That was one where we just learned, hey, guys, we have imaginary solutions. They're here. But for the sake of finding ordered pairs where they intersect, these ones don't on the real axis. So here we are going to stop short of using this, because remember what you'd have to do after this. Plug them into an equation to solve for y, and then the y's are imaginary as well. We're not going to go about doing them here, guys. In this particular section, if you have non-real solutions, we'll say that. No real solutions, especially when we solve by graphing. If they don't intersect, how are you going to find the imaginaries? You won't. And so that's why solving algebraically has its benefits. But here we are going to just stop short if it doesn't work. Now, I imagine if they do work, they're probably factorable, but we're going to go in whatever method seems necessary. So they have some methods where they say solve by substitution, solve by elimination. All of them seem to have y by themselves. You're probably going to see that a lot, but if they don't, I recommend getting y's by themselves and lining things up as need be, especially get things in standard form. All right, approximating solutions. When you can't find the exact, so they're going to give you exact ones at some point. Later they'll say approximate. We'll probably use a calculator. When you can't find the exact things, you can analyze output values to approximate. All right, this one here is not quadratic at all. This is an exponential function. We did these in chapter 1, I think 1.6, where we graphed exponentials. Sketch a graph of the system. You can see the system has one solution between 1 and 2 for x. It's not exact. Don't round. At least don't round. Say it's 1 comma 4. It's not what it is, right? Substitute 3 to the x power for y in equation 1 and rewrite the equation. Excuse me. So they plug this into here, and they have an equation that would say 3 to the x equals this, but they put everything on one side, set it equal to 0. That way they can graph this. This is kind of like that method number 1 that we did on section 4.2. Graph y equals this guy, and then find where they hit the x-axis. Because you don't know how to solve this equation algebraically, let this, y equals this, and then evaluate between here. They're doing rounding things. They're doing their approximations that way. I'm curious as to whether this is worth my time to do with you guys here. Maybe, because the book does it. Maybe your teacher's going to want this. I'm not going to assign it to my students, at least not in this particular year that I'm recording it. Or if you graph it, you can also use the calculator. I'll show you both, but I'm probably going to have to lean toward this. That's just the way I'm going to have to do it. Unfortunately for me, for time's sake. I'm starting this video kind of late. I don't want to do that. Anyway, so you get an x value, looks like, of about 1.194. How come? Because this is the number, the output, that gets closest to 0. Negative 0.0002. So you're going to have to work toward plugging in numbers until you get the closest to 0 possible. And you can tell because it's when you go from negative to positive or positive to negative as you go to, looks like 3 decimal places is what they want. So we're going to go with 3 decimal places, I guess. Work that out. I have other means of doing this with my calculator to just rough out the answer. And then we can plug this x value into the equation, into either equation, this one or that one, and solve for y. Either one, we should get the same y value out. That's about 3.173. So here's the ordered pair where it is. It's not quite 1 comma 4. It's more like that. Okay, recall you can use systems of equations to solve equations with variables on both sides. So last time we just saw one that was more like method number 1. Set it equal to 0 and I don't know, find the x-intercepts or whatever we did. Oh, well, we approximated numbers until it equaled 0. But here we can also have them on opposite sides. If we have this equation, an exponential, and this equation, a quadratic, here are versions of the graphs. It looks like they intersect at 2 spots. Here's the U-shaped parabola. Here's the exponential with an asymptote. And it looks like what they're going to go ahead and do is this time they're actually using the graphing calculator to graph it and using the intersect feature. So you're going to have to get your TI-83 for that. And honestly, I should have done that for the previous problem and found the zeros that way. But you find them this way, you plug them in. This one actually has an integer set, -1, comma, or rational set, 2.5. The other part's irrational. It looks like we're going to round some. They rounded to 2 decimal places. So we're going to have to work it out, figure out what to put in there. But there are a lot of different ways we can come up with it. Another method is using a table and figure out where they have the same y values out when you plug them in. I'm going to look more at this with you guys when we actually use the calculator, but I'm showing you visuals of it and figure out when they get as close to each other as possible, it looks like here. So not perfect. That's an imperfect version of that for sure. It's just approximations. They are a part of our stuff. Okay? So expect to see those problem sets. Expect those to slow us down quite a bit. That being said, I want to jump forward. Let's go ahead and look at vocabulary and core concept check numbers 1 and 2. Describe how to use substitution to solve a system of nonlinear equations, number 1. Well, what I'm going to do here is just describe it by saying isolate. I'm going to say set both y's, solve for y in both equations. Solve for y in both equations. That's not required, but it's recommended you do it in at least one, if not just the other. Then set x expressions equal to each other. And solve as you would other quadratic equations. Then substitute x values into either equation to solve for y. I ran out of room here to solve for y. Write final solution as ordered pairs. Solutions as ordered pairs. Oh, just ran out of room there. Let's see. Let's shift that just a little bit and pairs. All right. There we go. Lots of right there. Normally you'd write that on binder paper, right? All right, how is solving a system of nonlinear equations similar to solving a system of linear equations, and how is it different? Well, it's the same that you have different methods you can use. It's the same in that you can solve by graphing, substitution, and substitution and or elimination, and final results are ordered pairs. It is different in that you can have 2 solutions. You can possibly have 2 solutions. Now, you might remember that in a system of linear equations, it's possible to still have no solution because they can be parallel lines, and it's possible to also have an infinite number of solutions if they end up being the same line right on top of each other, which means technically you can have infinite number of solutions here, but not if one's a parabola and one's a line. That being said, you can have an infinite number of solutions with linear system. You can't have 2 solutions. See, the 2 solutions comes from and going through a parabola that has to bounce back, and so you can't have that with a linear set. Only 2, either 1, 0, or infinite. Here you can have 2, 1, or 0. I guess infinite, but you'd have to have the same equation, and you'd recognize it right off the bat, which we're not going to have here. Okay, let's go ahead. Let's see. I'm going to first go to myself and give myself a nice shot, a nice profile, and say, hey, how are you? We're going to go to numbers 3 through 62. Okay, so hold on to your hats. The first ones might be easier, the ones you're probably generally assigned or what have you, and then we'll dive into some calculator ones and probably word problems. They didn't mention real-life applications, but you can bet we'll either have word problems or strategy or critical thinking and things like that. So let's get ready, set, go. Numbers 3 through 6, we are going to match the system of equations with its graph, and then we are going to solve the system. So this one is a little less of doing the graphs yourself, and I think after that we solved by graphing is 7 through 12. So less doing it yourself and then more seeing what we have. So y equals, I wanted to use black. I'm even selecting black. Why didn't that work? Is that black? Yeah. Y equals x squared minus 2x plus 1, and y equals x plus 1. By nature, what we're looking for is a right side up parabola. paired with a slope, a positive slope. So it looks like that'll be B, right? I have a positive slope on A, but it's upside down. B, I have right side up, and it goes this way. This one's upside down with a negative slope and a negative slope with the right side up. So it looks like it's going to have to be B with that. They did mention to solve the system. Now, I'm not intending on drawing these graphs per se, so let's just look at what they have here. One point of intersection is 0, 1. The other point of intersection is 3, 4. So that's what we're looking for. That's 0, 1, and 3, 4. With perfect graphs like these, we can kind of figure that out a little more so, and that's what we have. All right, number 4. We have y equals x squared plus 3x plus 2. Oh, by the way, you could double check these for sure. Plug in 0. 0 squared minus 2 times 0 plus 1 is 1. 0 plus 1 is 1. Things like that. You can plug them in and see if they work. But all right, number 4. Y equals x squared plus 3x plus 2. And y equals negative x minus 3. We're looking for an upside down, right side up facing parabola and then a negative slope graph with a y-intercept. By the way, y-intercept of negative 3. I didn't mention that before. And that looks like D. Looks like D would be that one there with the right side up guy in the negative slope. So let's find the points of intersection. There are none. They don't intersect. We have no real solutions on these ones if they don't intersect. That means if I use the substitution method or something like that, I'd be taking a square root of a negative somewhere, probably in my discriminant, so I'm not going to play with that until later. Number 5. Y equals x minus 1, positive slope graph with a y-intercept of negative 1. Y equals negative x squared plus x minus 1, upside down facing graph, which, by the way, also has a y-intercept we can talk about. By the way, they have the same y-intercept, which means 0, negative. I'm not even looking at the graphs. 0, negative 1 is a point where these guys should intersect. So let's find that one. That is going to be A. Positive slope here, upside down right there. So this guy's A as your graph to match. And that has one real solution. It's the one that I just mentioned. 0, negative 1 is where they seem to hit. They hit tangentially there. 0, negative 1, which is that y-intercept that both of these have. So there are a lot of clues, guys, that you can see for which graph is going to be what. It's not just which directions they face. It's also those y-intercepts. That's a big one. Without actually graphing them, seeing the features for what they are. All right, number 6. Y equals negative x, process of elimination, we know this is going to be what? C. Y equals negative x plus 3 and negative x squared minus 2x plus 5. Negative slope for the line and upside down facing graph for that one, it is absolutely C. And they seem to intersect twice. One point is negative 2, 5. The other point is 1, 2. So negative 2, 5 and 1, 2. All right. Great. Okay. For these next ones, 7 through 12, we are going to solve by graphing, and we're going to do it in kind of that method where we graph them separately. We're not going to... we're going to do that. So number 7, we have y equals 3x squared minus 2x plus 1. Now, they are not favoring us with this kind of graph. I'm not really appreciative of the kind of thing they have. You're going to look at this negative b over 2a and say, what? The thing is, though, they probably say, use a table, man. I also hope, I'm going to check this right now. I'm going to try. I also hope I can use this one here instead of one of the tall graphs. I'm expecting our points of intersection to be somewhere between negative and positive 10, and our vertexes to also do the same stuff. Let's start with the bottom graph, though. It's going to be significantly easier to just graph. So this will be, let's use green for the bottom, blue for the top. So for the bottom one, I have a y-intercept of 7 and a slope of 1. So I just get to rise and run 1 like this. So again, graphing is what tends to slow these videos down, or use of calculator, and it looks like we're going to have to do both of these for a little bit. It's really this blue graph that I'm trying to decide how to work it best. I might have to work some table magic with it. Let's thin that out a little bit. All right, so there's the green one. The blue one, it does have a y-intercept of 1. At the very least, I can mention that. But where else does it intersect? This is going to be tough, because as far as like vertex goes, the x value is negative b over 2a. That's 2 over 6, or 1/3. And I would have been fine with a 1/2. A 1/3 is really tricky, guys. The 1/3 is, you have to judge where it is, and then getting other points alongside it. It's just, that's a chore. So I'll try. So 1/3, imagine it's kind of like that. That's the axis of symmetry, which means there's another point that reflects across that's at 2/3, right? We're already kind of hitting something that's a little the y value for that is also not a picnic either, so let's go ahead and take a look. It's funny that they start you off with this problem. 3 times 1/3 squared minus 2 times 1/3 plus 1. Maybe they said, hey, use a graphing calculator, but I don't think so. 1/3 squared is 1/9. 3 times 1/9 is 1/3. This is minus 2/3, which will be negative 1/3, and negative third plus 1 is 2/3. So it's pretty close. Your vertex is at 1/3 comma 2/3. It's pretty close to these other points right here. So 2/3 right there. So how do I do this best? Let's see. I'm going to go over 1 and up 3. It's going to be kind of like this. This is going to really be pushing my appearance of what we're going to have here. And then 1 away on this side. And then 2 away, we're going to go up 12. This is where it does fall off the graph, actually. 4, we'll do the best we can. 6, 7, 8, 9, and kind of 10, 11, 12, kind of like way up there, right? And then over here on the other side, we have a similar looking bit. So we'll approximate these. The guess is they're supposed to be hitting at integers. So, right? Otherwise, this thing won't really work out the way it does. So I'm going to make my best guess, and this is where I think the double checking is worth it. So my guess is we're intersecting here at negative 1,6 and here at 2,9. And I have no idea. That's just my guess with these. Let me actually do this in purple. Oh, that didn't let me separate. Give me one moment. There we go. Purple. All right, so that is at negative 1,6 and 2,9. Let's see if those are correct. I'm going to, let's do it with the linear one, right? Plug in negative 1 for x. Negative 1 plus 7 is 6. Boom, for y. So that you're going to trust it's... Oh, no, you do have to check it for both. You do have to check it for both. So 3 times negative 1 squared is 3. Plus 2 is 5. Plus 1 is 6. Okay, so that one definitely checks out. 2. 2 plus 7 is 9. Okay. Let's see if... It's really more important to check this one, right? This is the one where I'm not sure if it hits there. 2 squared is 4. Times 3 is 12. Minus 8. 2 times 2. Plus 1 is 9. So yes, that one checks out as well. So, all right, awesome. Like I said, I think if they're going to have a solve by graphing, it's likely that, we're going to be able to see where they intersect. And that wasn't a great graph as far as the fraction bits. So double checking, I think, was really important for it. Okay, number 8. Oh, I didn't, I'm sorry. Let's bring that thing down. So that was number 7. Haha. Number 8. Numero 8. Sorry if you go and scrub your problems by that and you're like, when is he going to hit number 7? What's good is you probably hit this timestamp on that section and you saw exactly where we started. All right, this graph will be much more favorable. Thank you. Okay. Here are our graphs. This guy I'm actually going to write vertex form by completing the square, if you don't mind. Any chance I get to be able to use that method, I prefer it myself over negative b over 2a. So this one here, when completing the square, it's 2x plus 1, and then plus 5 minus 1, right? Divide this by 2 and square it. So this factors down into x plus 1 quantity squared, and 5 minus 1 is 4. So here's the vertex form of this guy. That's my goal, using the vertex form and a stretch factor of 1, and there's the slope-intercept form of this guy. So let's go ahead and let's shrink that. I'm going to use the same size as this other one here. Oh, that didn't work. Give me one moment. Great. Okay. Let's go. Oh, because I locked it. That's why. Okay. Let's do the bottom again. Negative 2x minus 5. Y-intercept of negative 5 and go down 2, right 1, up 2, left 1. Plot as many as you can fit, please, because we have no idea where this other one is going to end up, right? Oh, wow, I forgot about that axis of symmetry. I'm not going to use axis of symmetry in the future if I don't have to, right? I had to do it for this other one, really, for a different reason. Okay, so there's one line. Now, the other one should be hitting on some integers that we're going to be able to feel out because of this one being an integers. This one is a vertex of negative 1 comma 4. And I already see where this is going. See, this graph goes upward. So 1, 1, 2, 4. If you've graphed with me in the past, then you know what I'm doing right now. 3, 9, I can't really fit. Probably somewhere up there. The point is, this graph is going to be right here. These graphs do not intersect. And that's unfortunate that these ones don't intersect. I wish the other ones didn't sort of. Actually, no, I'm glad the other ones did. We got to double check things. This one has no real solutions. Because they just straight up do not intersect. So yeah, we're bound to have one of those, and that's at least one of them. All right, number 9. Oh, let's save that for later. Let's write the equations first. Y equals negative 2x squared minus 4x, and then y equals 2. All right, let's just deal with that y equals 2, guys. That's a horizontal line across 2. The good news is if these intersect, we know what the y value is for the solution or solutions. There may be more than one. There may be none at all. And there may be one. Who knows, right? 2, 1, or 0. But we know the y values will be 2. I don't have to plug anything in for x. Well, I wouldn't. Excuse me. If we were solving this algebraically, I wouldn't have to know anymore. But we know where they should intersect if so. All right. This has a greatest common factor. I'm going to kind of use intercept form on this guy this time. I think it's worth it. So y equals, I can factor out a negative 2x out, and I have x plus 2. So I have x-intercepts of 0 and negative 2. Sorry, I'm pointing that wrong direction. 0 and negative 2 right here and here. That means the axis of symmetry is right in between. Oh, I do have to change it. Well, axis of symmetry is in between. AOS is x equals negative 1. So if I plug negative 1 into here, I'm going to get negative 2 times negative 1 times negative 1 plus 2 is 1, which is 2. So the y value is 2. That's where we hit. You can see where it's going upside down with this stretch factor of negative 2. Goes 1, 2, and then 2, 8. 2, 8 like this. And you see where it already intersects as 1, but let's complete our graph, please. So we get this on this side, this on this side. It just touches at one individual point. Clear as day, you can tell. It's at negative 1, 2. And we're going to go and put that. Negative 1, 2. All right, so I went factored form or intercept form for this one to get my x-intercepts, found the axis of symmetry in between, and went about that. So old school stuff, right? Negative b over 2a was totally in the cards. Didn't use it. Number 10. I will likely use it here. Y equals 1/2 minus, x squared. 1/2 x squared minus 3x plus 4. I'm very curious to show you the completing the square version of this one as well. Maybe I'll show you both, because why not? All right, so start with that bottom one in, as my nephew would say when he was like a year old, keen. Is he 6 now? Man, he's 6 years old. All right. I guess he was maybe 2 years old still when he was saying it. All right, so this is the bottom one, slope of 1 with a y-intercept of negative 2. Okay. The top one, I know I have a y-intercept of 4. Okay, that's cool. It's not my vertex. We have two options here. We have vertex of x is negative b over 2a. 2 times 1/2 is 1. 3 negative, opposite of negative 3 is 3. And then the y value, is the y value a fraction? The y value, maybe I won't do completing the square then. All right, so 3 squared is 9 divided by 2 is 9/2. So we have 9/2 minus 9, which is negative 9/2, plus 4. Negative 9/2 is negative 4.5. Plus 4 is negative 1/2. So you have a vertex at 3, negative 1/2. Okay, so 3, negative 1/2 like that. So stretch factor is 1/2. Over 1, up a half. Half of 1. Boom, boom. We saw where that point hits. Oh, by the way, this point reflects across. This is 1, 2, 3 away, 1, 2, 3 away. Look at that. We know where the other point already hits. Over 2, up half of 4, which is 2. Over 3, up half of 9, which is 4.5. Boom, boom. That's what we get. Over 4, up half of 16, which is 8, which is right, I think, here. And sure, that's all I can fit, so I'm going to stop there. And let's get that beautiful curve going. That looks kind of straight-esque. But I see where these intersect at those two places. Okay, here and here. So we intersect at negative 2, 0, and 6, 4. Negative 2, 0, and 6, 4. I'm trying to decide. I might save it for number 11. I was going to see if there was another problem where I could do completing the square with another vertex form thing. I'll probably try it on 11, especially if, and I don't know yet, especially if I can get an integer y value out. So if I can, I'll show you the completing the square version. If not, I might still show you it, but I don't want to do it twice, so I'll save it for the one where I can potentially get an integer. Okay. Green. Let's plot the green. All right, so number 11, we got these two equations here, really testing our ability to graph things with different kinds of stretch factors again, or use a table, however you go about your graphs. Y equals 2x is also 2x plus 0. 0 is the y-intercept, and we rise 2, run 1, like so. Here's the first guy. Okay. The second guy, we'll start with that negative b over 2a, mumbo jumbo. The vertex x is negative 2 over 2 times 1/3. That's negative 2 over 2/3. Now, that means it's the same thing as negative 2 times 3 halves. Negative 2 over 2 is negative 1 times 3 is negative 3. All right? Oh, good. I think we're going to get an integer on this one, which means I can show you the other version. Or I feel comfortable in showing you. 1/3 times negative 3 squared plus 2 times negative 3 minus 3 is 9/3, which is 3, minus 6, which is negative 3, minus 3, which is negative 6. So your vertex is at negative 3, negative 6. Okay? So negative 3, negative 6. All right, we found a point of intersection, and it might be the only one. Who knows? Who knows? Looks like it's not. We're probably going to have another one. But the vertex is where it hits. Now, if you wanted to do an alternate take on this equation and going to vertex form, let's do it down here. Boop, boop. An alternate take there. This was 1/3 x squared plus 2x minus 3. Y equals 1/3 x squared plus 2x minus 3. Using completing the square, you'd have to first factor out this 1/3 from the first two terms, x squared plus 6x, like that. So 1/3 of 6x is 2x. That's what we get. This negative 3 is going to stay out here, and I will subtract 1/3 of whatever I get here. That's where it gets a little tricky, is that this thing multiplies by the same 1/3. So this number is 9. Divide that by 2, square it. So this number is also 9. Notice how this multiplies by 1/3. So does this. Notice how I add here. I subtract there. That's the tricky part, but otherwise I kind of prefer this method if there's no fraction issues. This is x plus 3 quantity squared. 9/3 is 3. Negative 3 minus 3 is negative 6. There's your vertex form. That vertex is at negative 3, negative 6. Same-ish as before. So you can use the completing the square version, but it starts by factoring that thing out, not of the negative 3 itself, and you also have to multiply 1/3 by that other portion as well. So I'm glad I showed you it. There it is. Anyway, we have a stretch factor of 1/3, so let's go and do that. Over 1 up 1/3 on both sides. Over 2 up 4/3. I'm going to do all of them because I don't know where it's going to hit. Over 3 up 9/3, excuse me. Over 3 up 9/3, which is 3. Over 4 up 16/3, that's 5 and a third. You probably remember this from chapter 3 days. Over 5 up 25/3, that's 8. That's 5, wait, what was this? 5, 6, 7, 8 and a third. And I think it's the next one. Over 6 up 36/3, which is 12. 12 up from negative 6 is positive 6. And yes, we hit it there. I think at that point we can stop. 49/3 is 16 and a third. Actually, that would go just off the graph at 10 and a third up from negative 6. So that's good. Okay, points of intersection. We actually hit at that vertex, as you saw. Oh, that's not purple. Here, and then there as well. So the points of intersection are negative 3, negative 6, the vertex, and 3, 6. Cool. All right, we'll take it. That's number 11. Yeah, we're definitely going slowly on the graphing portion. I assume substitution and elimination will have its place. That's a lot faster than these ones. All right, new page, number 12. Hopefully they didn't save the hardest for last. The first one's been the hardest one for graphing. Oh, well, I spoke too soon. Y equals 4x squared plus 5x minus 7. Ugh, come on. And then y equals negative 3x plus 5. I'm even uncertain whether these things will fit on the graph the way that we want them to. I have no idea, but oh boy. You're negative b over 2a. If you thought that I didn't like 1/3, here we go. Green and blue. It's just mean, right? It's just mean. Why are you doing this with graphs? I don't want to complain to the book, but hey, book. I'm glad I'm only making this video once, you know? I'm not going to make my students do this, bro. Down 3, right 1 from 5. The line is fine. There's no problem with the line. If your teacher gave you this problem, they didn't look at the problem hard enough. See, I like to make videos before I assign things to students, so I know full well what kind of problem I'm giving them. And this one's going to be mean. Here we go. No completing the square this time. No, sir. We're going to use negative b over 2a. But even then, axis of symmetry, negative b over 2a. That's negative 5/8. Okay, here comes our line. Since I don't have to make any more after this. Let's make the axis of symmetry of negative 5/8. Might as well look like negative 1/2, sort of. Maybe I can do that one tick over. It's negative 0.625 if you want me to impress you with the decimal equivalent of that. I'm trying to, there we go. There's a good negative 5/8. I'm going to treat it kind of like negative 1/2. Let's see if the fraction, let's see if the y value holds up and is not a fraction. So 4 times negative 5, yeah, I think it's going to be a fraction. Negative 5/8 squared plus 5 times negative 5/8 minus 7. Where are we going with this one? That's 25 over 64, and 4 over 64 is 1/16. So it's 25 over 16 minus 25 over 8. That'll be negative 25 over 16 minus 7. Now 7 is going to, I'm going to multiply by 16 over 16 there because we're about to do negative 25/16 minus whatever this is over 16. 7 is 112? 7 times 16, 112? Yeah. Minus 112 over 16, which is negative 137 over 16, which is close to 16 times 5, 6, 7, 8, 8 and 11/16. Did I do that right? I have my calculator up. Let me try that. 16 times 8, 9/16. So I'm going to write the mixed number for my sanity. I know what I'm looking at. Negative 5/8 comma negative 8 and 9/16. And here's the thing. 9/16 is even closer to 1/2 than 5/8 is. So I really don't need that discrepancy of that thing. I'm just going to plot as is. So negative 8 and 9/16. It's even closer to 1/2 there. So, okay, so I'm going to treat them kind of like halves, if you don't mind. Our approximation will be close enough for us to figure out our graph. At least it fits. So I'm going to go over 1 and up 4. I guess from here it's not terrible, but just because my approximations are to me what they are. And then over 2 up 4 times 4, which is 16. Now 16 up from negative 8 is positive 8. And we're just going to go 7/16 down from that. So positive 8 and then just a little bit down like that. As we're 5/8 over. And then over here, 1, 2. Yeah, sure, close enough. Oh, this will go out of reach. Oh, shoot. Okay, this problem isn't good. Let's replace this graph with another one. My bad. That's not good. All right. No fun. Okay, let's see if I can replicate. I have to redo that. That is so mean. This is so cruel, guys. I apologize. I did not know. I'll attach both pieces of paper there. If you started graphing and you're erasing or doing whatever, you can probably follow along with me from here. If your teacher gives you this problem, just tell him or her. Why? What was the first one? Negative 3x plus 5. Well, if it doesn't fit on here, then I'm going to have to make my best guess at what they're trying to hit. I'm sorry about that, and unfortunately I'm not editing that part out because it would be too choppy. It's with too many other things in the way. Let me graph this axis of symmetry before I do the other part because I have to change the parts afterward. So, let's go green. Yeah, already 45 minutes in the video. I'm only on number 12, but like I said, these are going to be one of the longer sets of problems that we have, you know. Okay. So we got that. Negative 8 and 9 16ths. It definitely fits on this graph, right? So here. Okay. 1 comma 4. Stretch factor was 4. So 1, 2, 3, 4. 2 comma 16. That was near the 8, right? 8 and 7/16 down from there. Of course. It's about right there. All right, 3 comma. Now, I probably can't fit what I want to plot here, which is no better, but at least we'll see where they kind of intersect. All right, we'll get that idea. It must be this point or that. I can't. 3 comma 9 times 4 is 36. So going 36 up from negative 8, it won't fit. This only goes up to 17 for me. So it's around 27 something. It's another 10 higher. It goes super sharp though. That's the point. So if it goes up to like there, like yoinks. Remember it's between here. It goes straight up from here. So like yoinks up there. You can imagine how sharp that thing's going to go. And how sharp? Probably going to hit that point. So this is something I'm going to double check with later. That's just my guess. We had a y-intercept, by the way, of negative 7. That's not too helpful, but we did have that as another for sure. All right, I'm going to do my best guess version of this graph and assume that it's going to hit that to begin with and kind of see what happens as a result of that. That seems to make the most sense. So if it hits there, then sure, on the other side, it's going to have that other version of that. Just nice and sharp and downward. And it looks like I forgot to even try and actually hit a point, but it looks like it should be hitting this point right there as well. So this is one of those double checking ones, yeah? Okay. Let's look at that point and that point. So my guesses are negative 3 comma 14 and 1 comma 2. 1 comma 2. All right, let's try those and see if they work. They should work for the linear one. That's the linear equation. My concern is this top one. Negative 3 squared is 9 times 4 is 36. Minus 15 is 21. Minus 7 is 14. That one does check out. 1 comma 2. 1 squared is 1 times 4 is 4. Plus 5 is 9. Minus 7 is 2. That one checks out. All right, so those are the two answers there. I had faith in 1 comma 2 was this other one. I just needed to be sure. At least they gave us integers where they do that. We'll approximate things later. Okay, and that's the last one. Now, all the things that I said about these problems are mean and stuff like that. Listen, if you use a table, you'll figure out where they do intersect, and that's fine. Always go with a table if you feel you need to. I'm going off these methods for the sake of normal problems that you'd be assigned in other situations where you practice doing what you've been practicing in the past. At least with me. Okay, guys, we're going to move on to numbers 13 through 18 where we solve by substitution. These ones should go significantly faster when it comes to what is being presented with you. The y's are by themselves and solved for, which means our goal from here is just to do a straight substitution of one expression in for the y in the other part. As in, x squared plus 4x minus 5 will take y's place up in here, and we're going to have now a full equation that says x squared plus 4x minus 5 equals x minus 5. This replaced y, and now the equation only has x's in it. So our goal is to first solve for x. I'm going to use means of subtract x over, add 5 over, and you get x squared plus 3x. Looks like equals 0, because negative 5 plus 5 is 0. And we can solve using any method of choice. I really like solving by factoring. I have a GCF of x times x plus, x times x plus 3 equals 0. And by zero product property, x would either equal 0 or x equals negative 3. So we got two values for x, but you just saw all the points of intersections that we did solving by graphing. We, of course, need to also solve for y. So let's take these up here, and let's say for x equals 0, let's substitute. Listen, you can choose either equation. Does not matter which. I'm going to use this one. If x equals 0, y is 0 minus 5, which is negative 5. And if x equals negative 3, y equals negative 3 minus 5, which is negative 8. The idea, once of course, is you could plug in negative 3 into either equation, you'll get negative 8. You can plug 0 into either equation, you'll get negative 5. So your two ordered pairs for your answer are 0, negative 5 and negative 3, negative 8. Let me find my water bottle. Give me 1 sec. I think it's right over here. Got it. I'm going to also fix my camera a little bit here. Okay, that is number 13. Hey, really fast, right? So, as long as they're solvable, well, if they're not solvable, it'll probably go even faster. But as long as they're factorable, and we don't have to use like this whole quadratic formula bit, we should be pretty good. So y equals 6x plus 3. All right, you just saw in the previous problem what we did here before. We set 1 equal to that y, etc., etc. So we can write 6x plus 3 equals negative 3x squared. This problem's good to have it set up this way, because if I add 3x squared over, get it positive, we have that. Now, everything can divide by 3. Please go ahead and do that. Have a GCF factored out. Divide by 3, and we got this guy here. This is a perfect square trinomial. This factors into x plus 1 quantity squared, whether you call it solving by factoring or square roots. Take the square root of both sides. You say x plus 1 equals 0. Therefore, x equals negative 1. There will only be one solution to this here. The y value is found by substituting negative 1 into x in either equation. Pick your poison. Negative 1 squared times negative 3 is negative 3. Or negative 6 plus 3, boom, is negative 3. So your final ordered pair solution for that is negative 1, negative 3. Just one solution. If I graphed, that's where those two lines, or the line intersects with the curve. All right, number 15. Substitution is my preferred method among everything here, although graphing has its merits for visual sake. Y equals negative x plus 7, and y equals negative x squared minus 2x minus 1. See, why didn't they let us graph these ones? Yeah. They did for a couple. All right, so let's let one equal the other. I'm going to do the top one, because I'm going to add. I'm really thinking about just adding that x squared over. That's really my thought process of that. So if I add x squared over, boom. If I add 2x over, negative x plus 2x is 1x. Add 1 over, 7 plus 1 is 8. Okay, guys, this one's not factorable. No two numbers multiply to 8 and add to 1. I see the picture for the next part of this as well. You find other means to kind of solve. I'm going to look at quadratic formula as that instance in this case. If I use quadratic formula, I want to really begin with that discriminant, especially because I raise suspicion that perhaps this is just no real solution if it's not factorable. And there's a reason to raise that suspicion now when you see b squared minus 4ac. You get 1 minus 32, which is negative 31. We will not proceed forward on this set of problems and get the IA solutions out from here. From here, we'll say no real solutions. Taking the square root of a negative, right? That's not solving for x. I found the part in the discriminant where we'd be taking a square root of something, and can't take square root of a negative and get real solutions out. We're done. So each problem so far, we've seen a 2-solution case, 1-solution case, no solution case. Let's see where they go from here. Y equals negative x squared plus 7, and y equals 2x plus 4. Let's set 2x plus 4 equal to negative x squared plus 7. I will add x squared over, don't mind if I do. And let's subtract 7 over to get that minus 3. It looks factorable. Two numbers that multiply to negative 3 and add to 2 are 3 and negative 1. If x plus 3 equals 0, then x is negative 3. If x minus 1 equals 0, then x equals 1. Okay. If x equaled, let's just go down. Let's proceed downward. If x equaled negative 3, let's use an arrow. Y equals 2 times negative 3 plus 4. I'm going to use the bottom equation. Negative 6 plus 4 is negative 2. And down here, y equals 2 times 1 plus 4, which is 6. So ordered pairs are negative 3 comma negative 2. And 1 comma 6. Another 2-solution case. So I'm expecting maybe a 1-solution case for the next one. Maybe. One of them should be 1 solution, one should be no solution. That's my little anticipation. Number 17. Y minus 5 equals negative x squared. Okay, this one does not have y by itself. Now, that's not in itself inherently a problem. You just got to make sure that you don't, I mean, this one, it's, okay. Just make sure you don't substitute negative x squared in right there. That doesn't work. You can substitute 5 into here, but it'll just go in for y. So, you know what? Maybe I don't get y by itself here. I plug in 5 right there. 5 minus 5, I get 0, right? So this will become, you know, it's 5 minus 5 equals negative x squared, or 0 equals negative x squared. Now, I wouldn't take the square root of both sides yet. I got a negative x squared. Probably makes more sense to say x squared equals 0. But listen, x equals 0. There's only one kind of answer there, and that's the only one. And, hey, it was one solution. Now, what's the y value? I say no more, guys. It's 5, right? It's the only one that's possible that we get from that. I don't have to plug in 0 into this and figure the thing out. Y equals 5. That's the other one. So 0, 5 is the solution set. And even if there were 2x values for it, they would intersect at y equals 5. That's the only possibility that we'd have there. Okay, good. I like that these are going pretty swimmingly, and I get to have a good discussion while I'm just writing them out. No solution case? Let's find out. Y equals 2x squared plus 3x minus 4, and y minus 4x equals 2. Okay, in the same vein of we don't need to get y's by themselves, only make sure that you find the one where it is by itself and substitute into the other one. So at the very least, make sure you're doing that. So 2x squared plus 3x minus 4, and then there's still that minus 4x, right? This still exists. So whether or not you moved it over, I'm not moving it over because I don't really need to. I just got to combine like terms anyway, set it equal to 0. 3x minus 4x is negative 1x. And then subtract the 2 over, I get a minus 6 there, and there's your quadratic. Now, is this factorable? I'm curious. I'd love for it to be factorable. Let's give it a shot. If so, I'm going to try 6 and 1 or 3 and 2. I'm more leaning toward 3 and 2, or 2 would have to be there if possible. Let's try that. Negative 4 plus 3 is negative 1. This is factorable. This is factorable. So you have methods that you can choose. Factoring are probably quadratic formula. I'm going for that one. Negative 4 plus 3 is negative 1. So this is the factorization. Awesome. Good, good, good. So this is not a no solution case, y'all. This is a real solution case here. So negative 3 halves, negative 1.5, if you will, is one of your x values. We will need to substitute that into one of our problems here. Which is one of the reasons why you might want to set y by itself, by the way. If you consider, if I do, this time I am going to add 4x over because I'm just going to go ahead and substitute it into that one, right? Anyway, this other one, guys, is x equals 2. Okay, if x equals 2, then y equals 4 times 2 plus 2, 8 plus 2 is 10. If x equals negative 3 halves, y is 4 times negative 3 halves plus 2. 4 over 2 is 2, and 2 times negative 3 is negative 6. Negative 6 plus 2 is negative 4. It's not terrible. Not a fraction on that last part. So your final solution set, you got negative 3 halves comma negative 4. Not one I would have liked to graph with for that involved. I don't know what that would have hit as an x. And then 2 comma 10. And 2 comma 10. I don't think I boxed them separately before, but there it is. Okay, that is solving using substitution. Let's move forward. And let's solve by elimination. 19 to 26. All right, there are 8 of such problems, which I don't mind. The more of these kind, then the less of other kinds, right? What are we going to? Number what? 62? Oh, it's going to be a long night. All right, y equals x squared. Even after I finish this set up to 26, I'm still not halfway done. Think about it like that. X squared minus 5x minus 7. And the other problems are probably longer. They probably have calculator stuff. Y equals negative 5x plus 9. And I'm probably the only one doing the problems. Your teacher's like, I'm not teaching you anything beyond 26. I'm not with my students. All right, we're going to use elimination this time, guys. Now, this one has the... You're probably going to like this one a lot just because y is already by itself here. What I'm going to do in each of these is... Again, the elimination idea is you're going to add or subtract down these lists. Now, our goal will be to subtract because we're going to cancel out y's. What you probably, I'm going to rewrite them actually. What you want to probably first do to avoid any mistakes is line up terms. So like negative 5x is here and 9's there. Nothing combines with x squared and the y's are of course lined up. I am going to subtract down these lists though, which means change every sign. Subtract this y, add this 5, and subtract this 9 like that. So you treat these as they are. Y minus y is 0. 0 equals. X squared is not subtracting or adding with anything. Negative 5x plus 5x is also 0. So these kind of canceled and canceled. And then negative 7 minus 9 is negative 16. So we work off this equation. Our goal is to eliminate y's, get equal to 0, solve for x the rest of the way. You can solve using square roots or factorization. I'm going to use the square roots version. Add 16 to both sides. Take the square root of both sides. You'll get x equals plus or minus 4. Now remember, those are two different values, and we still have to solve for y given that. This is where you can use either equation. Of course, I'll probably use that bottom one. So we're going to say y equals, if x equals 4, y equals negative 5 times 4 plus 9. Don't write plus or minus 4. Have them separate. Negative 20 plus 9, which is negative 11. And if x equaled negative 4, we'll have y equals negative 5 times negative 4 plus 9, which is 20 plus 9, or 29. So with that in mind, we have 4 comma, sorry for the kind of rough dancing around everything, 4 comma negative 11 and negative 4 comma 29. I think everything worked out properly for that problem. All right, solving using square roots and using the elimination method. That was number 19. Number 20. I'm going to start by writing them kind of lined up to begin with. Makes most sense. So y equals negative 3x squared plus x plus 2. Let's line up the x terms together here. So y equals x plus 4. Now, once again, a subtraction will be had. Minus, minus, minus. Change all those signs. That's not a requirement, but that's what we're doing. We're subtracting. So y minus y, 0. Negative 3x squared is right here. X minus x, 0. They have to be canceling out a couple times here. 2 minus 4 is negative 2. Okay, I'm going to add the 3x squared over. Get 3x squared equals negative 2. And divide both sides by 3. X squared is negative 2/3. Taking the square root of both sides here will lead us to taking the square root of a negative. You've heard before that we would kind of stop in that case. No real solutions. No real solutions, taking the square root of a negative. We're not dealing with the imaginary versions of that. And yeah, that'll just be it for that problem. That's all I'm going to do on number 20. Number 21. Y equals negative x squared minus 2x plus 2. And y equals, and it looks like we're never really combining with x squared. So one equation is quadratic, one equation is linear. We're just going to have to deal with that appearance. Y equals 4x, that's not very lined up, 4x plus 2. Let's subtract down this list, change those signs, negative and negative like that. That's a minus now. And y minus y, 0. That's not going to change, right? Negative x squared, that's minus 6x. And this is 0, so plus 0 there, that's gone. Let's kind of make those positive, add those over. X squared plus 6x equals 0, and solve by factoring. I got a GCF here of x. So x can either equal 0 or negative 6. Sorry if I'm going fast through things that we've been doing since chapter 2. Apologies. Sorry, but not sorry. I value my time. If x equals 0, let's go to the original equation that said 4x plus 2. 4 times 0 plus 2 is 2. And on this one, we'll have 4 times negative 6 plus 2, which is negative 24. Negative 24 plus 2 is negative 22. There's maybe purpose to not writing that subtraction if you want to preserve what the original problem looked like, in which case I didn't. But if you remember what it was, or you can see through your markings, then you're all good. So 2 solutions that time. Great. We got it. All right, number 22. Last one on this page I'm going to write. Y equals negative 2x squared plus x minus 3. And y equals 2x minus 2. Let's subtract. Maybe for the last 4, I won't write the subtraction and just see how we do. I don't know. Depends on how it looks to you guys. I'm comfortable with it. I just don't know if you guys are. Y minus y. What's ironic, what's funny is if you take a look at any IM3 videos that I make on what's called polynomial long division, I don't do this. I don't change these signs, and I treat them as they are, and I say deal with it or do your own way, which is interesting because I don't do that here, or at least when I'm showing it. I don't know. Maybe it's just because you're 1 year advanced, and I'm like, you can see it for what it is. Anyway, see these for what they are. So I have, I'm going to add everything over. 2x squared plus x plus 1 equals 0. That doesn't look factorable to me. It's not. Not factorable. If you want to kind of confirm that there's probably no real solution here, let's go for that discriminant and do b squared minus 4ac. And you'll see that we get 1 minus 8, which is negative 7. No real solutions in this case. Assuming I didn't talk through a problem incorrectly on the subtraction phase, we changed all those signs up. Those are the net values that we got. That seems to work out. So no real solutions for number 22. They just don't intersect. Number 23. Y equals 2x minus 1. All right, check this one out. I'm going to give myself some space here. And y equals x squared. I want to put that x squared first and front it. All right. Let's try and subtract without writing minus signs. Y minus y is 0. 0 minus x squared is negative x squared. 2x minus nothing is 2x. And then negative 1 minus nothing is negative 1. So that works out in that form. Kind of change the signs. Add this over. Subtract that over. Add this over. Get your x squared positive. Please get your x squared positive when you solve algebraically. Don't be at fault because you didn't do that. This is a perfect squared trinomial of x minus 1 quantity squared. Therefore, x equals 1 is your only possible solution out of this thing. It's your repeated root. If we substitute 1 into either equation, I actually like this one. Y equals 1 squared, which is 1. So your ordered pair is 1, 1, which is the only 1 that exists. That is 23. Number 24. Y equals... Let's try that subtraction without writing subtraction. Y equals x squared plus x plus 1. And y equals negative x minus 2. All right, how daring are we here? Let's check it out. Y minus y is 0. X squared minus nothing is x squared. X minus negative x. That's x plus x, which is 2x. Yes, I'm subtracting without changing the signs. 1 minus negative 2 is 1 plus 2, which is 3. Whew, there's that. All right, x squared plus 2x plus 3 equals 0. That is non-factorable. I'm going to do completing the square this time because I have an even thing. So I'm going to subtract 3 over. I'm going to try and complete the square. Subtract 3 over and figure out what we add. Divide by 2 and square it, you get 1, and you can see where there's an issue this way as well, negative 2. As far as the taking square root bit goes, we're taking the square root of a negative. No good. So we got no real solutions. They have quite a few of them here. For 8 problems, you'd imagine maybe 2 of them having that, but they're really stopping you short on having to do more than it. All these seem to have, oh, I spoke too quickly. Seem to have y by themselves. No. On these ones, you really do want y by themselves. There's a hiccup if you do not. You're not actually treating things for the proper signs that they are. So I'm actually just going to write these as they are to start with. And then we'll rewrite them when we line them up and such. Plus 4x minus 6. Excuse me. Okay, on the top equation, you know what? I'm just going to write the top equation just down below right here. We're going to rewrite it as y equals, now it's negative 2x. Subtract the 2x over, write it where it lines up. So this will be the system I'm dealing with, okay? Subtract these, you get 0. X squared minus 0. 4x minus negative 2x is 4x plus 2x, boom, and negative 6 minus 0. This is non-factorable. However, you're going to have solutions. They'll be real and irrational. Didn't know that we'd actually get that. I didn't expect it. But they're here. So let's deal with it. Let's see what we do. I myself am curious as to, I'm adding this 6 over. I'm curious myself as to how we're going to play with that. So here's 9 and 9. We'll do the best. Well, it's just negative 2x, so that's actually pretty simple. So x plus 3 quantity squared equals 15. Okay, so they're doing this. Let's take the square root of both sides, and we'll get x plus 3 equals plus or minus root 15. So x equals negative 3 plus or minus root 15. Okay, here are the 2 different x values that you have, right? Now, the y values are based on plugging these in for x. Negative 2 is the one I kind of just want to plug this into. Negative 2x, rather. Negative 2 times negative 3 plus or minus root 15. And yes, I'm writing both of them just to, well, I'm going to separate them. Because you want to know which ordered pair goes with which. This is when I plug in negative 3 plus root 15. And here's when I plug in negative 3 minus root 15. Now, I want to distribute. We'll get 6 minus 2 root 15. Okay, not too bad. And then 6 plus 2 root 15. Okay, so your ordered pairs, we're going to write them as irrational, exact answers. We're going to have negative 3 plus root 15, comma, 6 minus 2 root 15. And listen, there's no obligation for the book to have done a problem like this beforehand for you, but it really seemed like that they would only present rational solutions for you so you wouldn't know what to do with a hiccup like this afterward. The other one was negative 3 minus root 15, comma, 6 plus 2 root 15. Now, what are those numbers close to? I'd have to work that out. I know that root 15 is close to 4, so negative 3 plus 4. It's a little close to 1, and this is a little close to, say, negative 7. That one, I know a little less so. 2 times 4, I don't know. I'm not going to deal with it. You can use a calculator if you'd like to round it, but I'm writing the exact answers there. Now, number 26. I wonder if they're going to do the same thing with this one or not. They are starting with not having a y set by itself, so there's that. Number 26, we got y equals 2x minus 7, and then y plus 5x equals x squared minus 2. All right, that bottom equation, of course, we're really interested in taking it and getting y by itself. So y equals x squared minus 5x minus 2, knowing that we're using elimination here, of course. And this one is y equals, let's line them properly, 2x minus 7. Through subtraction, we got 0 equals, and we got x squared. Negative 5x minus 2x is negative 7x, and negative 2 minus negative 7 is negative 2 plus 7, which is 5. It looks like, once again, that it's not only not factorable, but we're going to be dealing with irrational solutions. This time I will use quadratic formula, given that that is an odd linear coefficient. We have b squared minus 4ac, which is 49, minus 20, which is 29. For quadratic formula purposes, we're going to say x equals negative b, opposite of negative 7 is 7, plus or minus root 29 all over 2 times 1, which is 2. And these are the two different answers for x. Now, neither of these are very good. Oh, no, the top one's actually good. I'm going to use the top equation. I'm seeing ahead as far as what these are. It's actually not bad. It's going to look a lot better than x's, I'll tell you what. So let's do this. I'm going to kind of break this off, section it. All right. Y equals 2 times, we'll do 7 plus root 29 over 2. And then there's still a minus 7. 2 divided by 2 is 1. Boom, they're gone. Now you have y equals 7 plus root 29 minus 7. 7 minus 7 goes gone, and you're left with root 29. That's when you plug in 7 plus root 29. For 7 minus root 29, and guys, it's the exact opposite. The other one is going to be negative root 29 for the other guy. I think I got to show the work. Maybe you're like, I don't know how you did it. 2 times 7 minus root 29 over 2, and then minus 7. 2 divided by 2 is still 1. So you have y equals 7 minus root 29 minus 7. 7's be gone. You have negative root 29. At least now we can see what we plugged in, which one we plugged in. So your two ordered pairs are 7 plus root 29 over 2. Don't ask me what that approximates to. Over 2, comma, if I gave it time, I could figure out. Root 29. I know that's close to, that's somewhere between 5 and 6. And 7 minus root 29 over 2, comma, negative root 29. Now, I don't know who came up with the problem, but they're like, yeah, let's make that one kind of clean up a little bit. Good on them for doing it. All right, 25 and 26 are done. Excuse me. Now we're probably going to go to problems which actually spend more time. Error analysis, number 27. Describe and correct the error in solving the system of equations by graphing. So they say the solution, the only solution of the system is 0, 4. I beg to differ here. Now, they're correct. Now, let's guess that they also graphed this correctly. Y-intercept of 4, negative b over 2a, looking at other stuff. They probably graphed it properly. The issue is assuming this only has one solution. Our window range is so limited, you can tell that with this line here, if this line kept, going, boom, boom, like that, the parabola is going to curve up enough, and eventually you're going to find another place where it hits, right? So this graph, although they, let me kind of write this, type it as I say it. Although they graphed properly, the window range is too small to see the other point of other point of intersection. Since a parabola will always increase more sharper than a linear function eventually. Eventually that thing will curve up sharper. At this point it probably already started doing it, but eventually it's going to hit again. And what is that point? We got to figure that out. So I got to kind of do another thing with a graph here, and I'm going to do the tall one because I have no idea how tall it's going to go before it hits, which does mean we have to work out some negative b over 2a stuff. So let's go ahead and write out what those equations are. They said do it by graphing. So we have y equals x squared minus 3x plus 4, not the best thing, and y equals 2x plus 4. I'll tell you what, I'll go off their graph and what's correct so far. Clearly this one is already kind of set and it's pretty easy to do. So slope of 2 with the y-intercept of 4 looking like this. Let's hope it hits within this portion. Now, without looking too, I clearly don't need to go this far over. Without talking too deeply into it, I'm not going to play with the negative b over 2a stuff. It's looking like it's hitting. I mean, I'm going to kind of rough out where it's kind of hitting. It looks like it's hitting at 3/2, 1.5, comma, and then probably 2 3/4. I mean, I don't know if that's perfect, but it's kind of there-ish. I'm just going to use that, right? So we're hitting like there. The stretch factor is 1, so I got 1, 1 here. I got 2, 4 here. I got 3 and 9, 5, 6, 7, 8, 9. Probably after 4, 16 will be all good. So I'm glad I got the tall graph in here. And then 4, 16. So 10, 11, 12, 13, 14, 15, 16. I think it goes just out of range there if I'm adding that correctly. 17. Yeah, I think so. So right there for that one. Okay. So we got that graph. Let's rough that out. And let's figure out where that rightmost point is actually hitting. So we got that one at 0, 4. Okay. This other one, I guess it's hitting this guy right there. Boom. So we're finding it. We're within our window range this time. Within a window range to do this. So 0, 4 and 5, 16. So 0, 4 and 5, 16. I'm not going to guess and check that. That's looking pretty solid. Looking good. The point is they missed one. Okay. Do I have more room? No. All right, let's go to new page here, new page there. Another error analysis, number 28. Hopefully these solve using another method that's not graphing. Describe and correct the error in solving for one of the variables in the system. Y equals 3x squared minus 6x plus 4, and y equals 4. So look what they did. They took 4 and substituted it into x to solve for another y. So it means we're going to have to completely redo what they did. They substituted a y value in for x. You must solve for the x or x's that are solutions to the system using substitution or elimination or graphing, but of course this is, I think they want you to do algebraic, using substitution or elimination. Now which one am I going to do? I'm going to use, we've done less substitution, even though elimination might make more sense. I'm just going to go and use substitution. Y equals 3x squared minus 6x plus 4. Now, here's the good news, and I mentioned this from a previous problem. I know the y values for the system will be 4. I mean, it's not hard to figure out after, but the answers will be something comma 4 if there are solutions. Something comma 4 and something comma 4 if there are two of them. Absolutely, because y equals 4 is, one of the answers, one of the equations. As far as substitution goes, we're going to say 3x squared minus 6x plus 4 equals 4. Subtract 4 from both sides, you get 3x squared minus 6x equals 0. All right. GCF of 3x takes hold, and you get x minus 2 inside. Either x equals 0 or x equals 2. This is where you would substitute 0 or 2 into these equations, but I don't need to. I know the y value is going to be 4 as a result of this. So my two answers are 0, 4 and 2, 4. I'm always prematurely wanting to box. There they are. Okay, big error from them. I don't know how many times people would do that, but because there's a constant, it's possible to see that. Okay, 29. In exercises 29 to 32, I'm not going to rewrite the table, but I'll copy it. Use the table to describe the locations of the zeros of the quadratic function f. Locations of the zeros. All right, so in this first one, so they give you, okay, so it's a quadratic, a parabola, right? They give you one of the zeros right here. Excuse me, that's not correct. That is a y-intercept. You want to find where y equals 0. Y will equal 0 somewhere between x equals -4 and x equals -3, because your graph goes from negative to positive here. Somewhere 0 is hit on this continuous function. And same with this one. It goes from positive to negative somewhere between 0 and 1. So they said use the table to describe the locations of the zeros. The zeros are the values of x that give you a 0 for y. So somewhere between -4 and -3 and 0 and 1. Do I know exactly where? No. -3.5. I don't know. They just said, describe them. Somewhere between those two. It's where we go from negative to positive, etc. This probably helps you for if you do some of the calculator problems later, and gives you the idea of what you try and do with them. You try and find where it goes from negative to positive and get more precise as you move along. All right, number 30. Let's copy this one over. All right. Here we go between positive to negative. There, we hit 0 in between 1 and 2, and then we hit 0 between 3 and 4. So I think I'm just going to kind of copy and paste what I said here before. Somewhere between 1 and 2. It says my computer's running low in storage space. I thought... Okay, so I'm back. So my computer ran out of storage space. I didn't delete my old recording, my video that I did before this. So I think I ended at this spot. The only problem is, it doesn't matter to you guys when you see the video. I have to now, I don't have to edit the video, but I just have to merge these two videos together, which it just takes up time. So somewhere between 1 and 2, we go from positive to negative. Hopefully you heard me say all this. Positive to negative is 0, and between 3 and 4. 3 and 4. So I'm just copying and pasting this from the previous set. So all's taken care of there. Let me make sure my other file, before I keep moving forward, I think my other file is there, and I think I'm good to go. Hopefully I finish recording. How long was my first video? I can't remember. But hopefully I finish recording before, I run out of time. Okay, number 31. I don't know if there's a need for me to copy these down. You know what? I need to copy these down. Let's just look where we go from positive to negative. From positive to negative here, and then from negative to positive here. Now, there's something else that can be said about the whole somewhere between. I kind of mentioned it on the previous problem, or the first problem or whatever, is that we're probably closer to one number than the other. I don't think it's my go ahead to kind of say which one that is for sure, but somewhere between -4 and -3. I hope that's fine. But it's probably closer to -3 because this is closer, the -1 is closer there. That's not a guarantee though. The finicky part about quadratics is that they increase more sharply as you go. Or sharper, I keep saying more sharply. They increase sharper as you go. More sharply is fine. But, so I can't guarantee that as it goes sharper up to 3 away from there, that it's, I don't know if it's right in between, if it's closer to one or the other. It's kind of tough. All right, number 32. Now, the interesting part is doing number 31. That's halfway to 62. I know I did a lecture at the beginning, and I know that there were a lot of graphs early on and stuff, but we're about to do a lot of approximations coming up here. Now, this one, I think I have a lot more... Sorry, I'm going to look at these first. This one, I think I have a lot more leeway in saying that the one beat somewhere between 2 and 3, I think it's a lot closer to the 3. This one, that -9 is nowhere as near 0 as 1 is. Closer to 3. I don't know if they're approximating each time and giving you better results than what I'm saying. And then somewhere between 5 and 6, I can't state for that one, or corners, necessarily closer. That has that sharpening kind of effect to it that I have no guarantee on that one. Definitely closer to 3 on number 32 to me. Okay, numbers 33 to 38, we're going to use the method in example 4 to approximate the solutions of the system to the nearest thousandth. So because they stated that we use a method that they provide, we're going to go ahead and use that method. I believe that this is the method where we set everything equal to 0. Like we do a substitution, right? I'm going to take 3 to the x power. It's not 3x, it's 3 to the x power. 3 to the x power and substitute it into here. Set everything equal to 0 on one side. So, as in like, what did I just do? As in do like 3 to the x, I just did it again. 3 to the x minus x squared minus 2x minus 3 equals 0. So we have an equation. We're going to write a y equals version of this graph, basically come up with what the graphing equivalent of that is. And then we're going to plug values into that equation. Now I'm going to go more of a table format. So follow with me as I go to my graphing calculator, where I think I did a previous calculation of, yes, 16 times 8. So I'm going to create a y equals equation here. I'm going to go 3 to the x power, 3 to the x, minus x squared. This is where things go a little long, sorry. Minus x squared minus 2x minus 3. Okay. I'm going to go in its table format thing. Now, I have no idea. Well, actually, I'm going to look at the graph first, because I have no idea where it's going to hit. We have to find out where it hits the x-axis. So somewhere between 2 and 3, right? That's what this graph looks like, somewhere between 2 and 3. So what I'm going to do is I'm going to go between 2 and 3, and this is going to be my version of it. I'm going to plug in numbers. I'm going to plug in numbers between 2 and 3 and figure out where we go. Let's try 2.1. 2.2, and figure out when it goes from negative to positive. Let's try 2.5. It went positive, so somewhere between 2.4, 2.3. Okay, that was terrible for me to do. Okay, between 2.3 and 2.4, it goes from negative to positive, right? Now, it's kind of right in between. Let's check 2.35, somewhere between 2.3 and 2.4. It's positive there, so 2.34, it's negative there. It's closer to 2.35. I'm going to go to 3 decimal places. Let's go to 2.348. It's negative there. What was I looking at? 2.349. Wait, did I, am I doing this right? I think I'm doing this right? Wait, what was 2.35? Oh, 2.35 wasn't, oh, it's between 2.4 and 2.3. So I'm sorry, 2.39. This is what I got to check out, right? No. I forget where I am with things because these numbers show up as different values. Let's go to 2.35 again. 2.35, 2.36. Okay, somewhere between 2.35 and 2.36. My bad. This is why I don't like these problems. 2.354, 2.353, 2.352. 350. So right in between 2.35, I know I wrote 2.351, but it doesn't seem to keep those numbers. Oh, Oh, that's why it was overriding them. Okay. Between 2.35 and 2.351, it goes from negative to positive. Now it's closer to 2.35 because this number is closer to 0 than that number is. Hopefully that makes sense. I have to do 6 of these problems. So this is x is about 2.350. I'm still rounding 3 decimal places when I say that. I'll kind of try and promise to be better next time. In fact, I'm not going to plug in numbers like that. I'm going to use more of the table feature where I can scroll through it, but I have to keep changing the precision of my values when I find out as I'm between two numbers, but I can still use that. I'd really just like to use the 0 feature on the calculator, but they said use this other method, and I'm going to go ahead and do that. Especially when you get problems like the ones before it. Y equals 2 to the x plus 5, and y equals x squared minus 3x plus 1. Okay, we're going to do another kind of substitution thing here. 2, not 2x, 2 to the x plus 5 equals x squared minus 3x plus 1. Let's subtract x squared over. I keep doing that. Why do I keep writing x? Subtract x squared over. Add 3x over. Subtract 1 over, and 5 minus 1 is 4. So we have this equation. So let's write out that equation in our calculator this time. 2 to the x minus x squared plus 3x plus 4. And this time I'm going to go to this table and I'm going to do kind of an auto thing, but like we got to figure out where it's between. So on the graph, what if it hits more than once? I can't tell. I'm going to guess it only hits more than once. It's really close to -1. It might even be -1. Let's go to this table. Let's start at -1 and see if we're hitting 0 exactly. And if not, we'll move on from there. Not exactly. In fact, I expected it to be... oh, it's really close to there, though. Somewhere between -1 and -1.1. It seems to be a lot closer to -1.1 once it hits negative. So I'm going to start this time at... Check this out. We're going to start at -1.1. And now we're going to go by 0.01 increments. So that's what I'm doing here. I'm finding out when I go from negative to positive. Between -1.1 and -1.09, it goes negative to positive. So now let's go by 0.001, excuse me, to go to the nearest thousandth. And now we go from negative to positive here. Now that number, if you use scientific notation to make a smaller number for a positive, that is a positive number. That's 0.006. 0.00064, etc. It's going to be closer to that one. So negative 1.092 is the closest one to 3 decimal places. That will be the approximate answer to that. And I hope there's only one of them. I didn't zoom out to see if there's another one, but given an exponential, it's likely that's it. All right, so that's what I'm going to do for those ones here on out, if that's cool. All right, number 35. Number 35, we have y equals 2 times 4 to the x power minus 1. Do not turn this into 8. Order of operations means you do that first, and so we can't simplify that any further. 3x squared plus 8x here. So let's go ahead and do that same stuff as before. Let's just kind of do this in one step. 2 times 4 to the x power. We're going to subtract that 3x squared over. Remember that would have been on the other side. Subtract the 8x over, and the minus 1 is over there as well, equals 0. So I'm going to go off that equation. Let's play with it. 2, you got to see this. Guys, you got to see this. 2 times 4, again, don't turn it into 8. 2 times 4 to the x power minus 3x squared. Minus 3x squared. I think I'd rather graph. Minus 8x. I'd rather graph normal graphs. Minus 1. Absolutely. Let's figure out where this graph looks like here. Okay, this hits 3 times. I actually didn't expect that. So this hits 3 times. We got to find all 3. So the first one is somewhere between -2 and -3. So let's start around -3. Let's go by 0.1 increments. Let's check it out. So I'm guessing a lot of these are going to do that as well. Somewhere between -2.6 and -2.5. So -2.6, let's go by 0.01 increments. And we're now between negative 255 and negative 254. Again, we're looking for where it goes between negative and positive. Again, hopefully you see that's what I'm trying to do. Where it goes between negative and positive. And then negative 2.55. Let's go by 0.001 increments. And we got between here. So which is the smaller number? This one, 0.00234. Therefore, this is one of the x values, negative 2.543. Negative, I'm just going to write it here. You don't have to see it. Negative 2.543 is one of the x's where we hit 0. Now, the next one looks really close to 0. It's not going to be, well, actually, I think it is going to be 0 because of exponents, the way that exponents work. Let's try it. Oh, you get 1. 2 times 4 to the x. That's right. That's right. I was going to say, isn't 4 to the 0 power 1? Okay, so between 0 and 1, it goes smaller. So let's go by 0.1 increments. I was hoping for a freebie. So between 0.1 and 0.2, you can see it goes from positive to negative. So let's go at 0.1. Let's go by 0.01 increments. I assume you can do this on any of your calculators that you have with it too. You got to find where it hits between first. Now, I don't have, by the way, I don't have to use my calculator. I don't have to use the graph to see where I go in between. I can actually use the calculator portion there. I will for the next problem. Between 0.18 and 0.19, let's do that one more time. Sorry, my neck's bothering me. I have my calculator thing rotated too far over. Between 0.185 and 0.186, and it's closer to 0.185. This is the smaller number, so it's closer to 0. So 0.185, really close to 0. All right, there's 1. The final one. Oh, I just hit something. Oh, I know what I hit. The final one is between really close to 2. I wouldn't be surprised if 2 was the value. I don't know, but really close to 2. So let's go to 2 and go by 0.1 and figure that out. Am I looking at that wrong when I look at the graph when there's a 3? I guess, no, I guess not. I guess it's just zoomed out enough that it's hard to tell. From 1.8, let's go by 0.01. Oh, goes this way. So 1.85 something. 1.85. Let's see it. 1.854,855. Let's see. 0.007, 0.00. 1.854. X is about 1.854. Okay. All right. So those are the 3 solutions that we got for that one. That's what I wrote down there. Now, the only difference I'll do from other problems here is I won't go to the graph anymore. I'm only going to look at the table and see when it turns from positive to negative when I go by increments of 1. And we'll just find them for ourselves and narrow it down. So less of the visual to make sense of what we have, if that's cool. And more of that table use even, where you're just plugging things in straight up, right? We don't know until we find the values out. All right. Negative 5 to the x. I'm going to write this thing out first to say which side I'm going to go. I kind of like my to the x power thing being positive, so I'm going to add that over. So 5 to the x, and then I still have negative x squared and negative 4x. But I'm going to add 2 over, and negative 4 plus 2 is negative 2. It's okay to have the exponent positive at the cost of everything else being negative. Let's go back to our graphing calculator. Let's plug that in. So 5 to the x. 5 to the x minus x squared minus 4x minus 2. All right, now I'm going to go straight to table. I'm just going to start at 0 and go by increments of 1. And let's figure out where we go positive to negative and so on and so forth. And I'm not going to assume we only do it once. In fact, we don't. You can see here we go from negative to positive between negative 4 and negative 3. We go from positive to negative between -1 and 0, and is that it? And oh, and we go from negative to positive between 1 and 2. So there are another 3 here. Are there more? It's unlikely. We're going pretty sharp after that. So, all right, between negative, what was it? Between -4 and -3. Let's start with that. From -4, we'll go by 0.1. And we got from -3.5 to -3.4. So from -3.5, let's go 0.01. And we'll hit positive again. Between -3.42 and -3.41, let's do one more. -3.42, let's go by 0.001. And we get positive between this guy and this guy. Now, this is scientific notation, like I said, which means you're looking at something likely smaller. Oh, you know what? That's not necessarily true. This one's actually, because it's negative, it fits. This is negative 0.009. And this is positive 0.001. The only reason they have to write scientific here is because it's a negative symbol. So I'm guessing this is actually the closer one. So, okay. So negative 3.415 is the first one. So x is about negative 3.415. Okay, I just wrote that down. All right, the next set, I don't remember what it was between. The next set was somewhere between -1 and 0. So let's start at -1. Let's go by 0.1. Between -0.5 and -0.4. Between -0.42 and -0.41. I think this is one of the same things, only this one's to the 10 to the -4th power. I think this one's going to be the smaller one. So -0.415. I'm just going to go ahead and write that. X is about -0.415. Okay. All right, there's one more. Whoops. I'm not looking at a graph anyway. 0, 1 more between, what was it, between 1 and 2? Between 1 and 2. I think it's going to be closer to 1 here. Not really. It's between 1.4 and 1.5. So you can see where that sharpness of the graph really does change things. Of a parabola, that is. It's not even a parabola. It's a exponential. Maybe that's why it's so sharp, because it's exponential. It's closer to 1. So 1.4 still. Okay, so 0.001, last set. Between 1.404 and 1.405, it's closer at 0.001 versus 0.007. Okay, so 1.405. Hope not all of these have 3 the rest of the way, because that's a lot of work. I mean, I'm saying, just for the sake of me doing every problem, that's a lot of calculating to do. Approximately the solutions of the system to the nearest. They say to the nearest thousandth too. I was thinking, am I doing overkill by doing 3 decimal places? No. The only thing I could do faster, and it would be significantly faster, is to just find the zeros on the graph. But they're saying use this example in the way that we, are doing it. Okay, 37. Y equals -x squared minus x plus 5, and y equals 2x squared plus 6x minus 3. I actually would favor using elimination this time, just because they're all quadratics and like and such and such. So let's subtract down this list. Y minus y is 0. -x squared minus 2x squared is -3x squared. -x minus 6x is -7x. And 5 minus -3 is positive 8. But I'm going to still write it like this. Even if I'm solving by approximating using this other method, I'm going to swap all the values out. So let's graph this y equals this. We know this time there will only be at most 2 solutions because it's a quadratic. In fact, there will be 2 solutions because of the nature of the y-intercept and the stretch factor. So I got a 3x squared plus 7x minus 8. So I know there will be 2 solutions. I just don't know where they are. Let's go to the graphing calculator and look at what I'm about to do. y equals 3x squared plus 7x minus 8. Let's do a window from 0, go up by 1s, and see what we have rocking. So we go from positive to negative between -4 and -3, negative to positive between 0 and 1. So -4 and -3. So -4, let's go by 0.1. Positive to negative between -3.2 and -3.1. And then between -3.18 and -3.17. And then finally, as close to the thousandth, between -3.174 and -3.173. It looks like it's closer to -3.174. Okay, so I got one of them. The other one was between, I think, 0 and 1. Or something. Let's pretend it was between 0 and 1. Let's see if that works. Yeah, So between 0.8 and 0.9. Between 0.84 and 0.85. And 0.008 versus 0.003. 0.84. 0.840. 0.840. That's the closer x there. And I want to write that third decimal place of 0 just to kind of bury the hatchet and say precisely I was actually closer to the 0 than I was to a 1, or you know, something like that. Okay, and then the last one from this set, number 38. I think as we did substitution now quite a few times, let's go back to kind of elimination again. Y equals 2x squared plus x minus 8, and y equals x squared minus 5. If we do elimination again, 0 equals 2x squared minus x squared is x squared. We've got a plus x there. -8 minus -5 is -8 plus 5, which is -3. It's not factorable. So this is one where I'm going to work that out. There should be two solutions again. Let's figure them out. Now remember, for quadratics, you know, quadratic formula and stuff is something we can use. We're using the calculator for the approximated version of this because it's what's requested. If we have a chance to do any of that other stuff later, we will. So, but where are they? Sorry, you can't see this, what I'm typing. So I typed in the equation, by the way. I did this. I'm going to check and find out between from 0 and onward where we go negative to positive, etc. At least these numbers are clean. From -3 to -2, and between 1 and 2. So from -3, -3. It's really close to that -2.3. I'm going to start actually from there, -2.3, and I'm going to go kind of upward. Excuse me. So let's go upward. Still closer to -2.3. As we go to 0.001. And now we see some discrepancy. Oh, I didn't start from -2.3. -2.3. There we go. Okay, so let's see. That should be closer. That's 0.0008. And this is 0.002. So 0.0008, one's positive. -2.303. So -2.303 is one of them. The other one I think I said was between 1 and 2. So 1. Excuse me. This is the other one. So maybe this is positive 1.303. I'm going to make that guess. 1.303. Because I think there's symmetry in this one. And let's see if that kind of works itself out. Yeah. 1.303 does the same thing on this side. So cool. Because this is more of a thing. It's more of a normal quadratic with that symmetry. And there's symmetry. It's how quadratics would generally behave. So why did this one not as much? Because it was a 3. Because the fraction, it didn't have an integer. I'm not going to talk about it. Just this one just works out better. All right, so that was those ones, and those took a long time. Number 39 to 46, solve the equation, round your solutions to the nearest hundredth. It says C example 5. I was going to say, okay, I'm just going to use quadratic formula and go. What was example 5? Give me one moment here. Example 5. So we get to use the graphing calculator. Probably even better. We get to use the graphing calculator for these ones here. Let me go back to the page. And just find where they intersect. So, cool. I'll do that. All right, so number 39. I kind of wanted to use the quadratic formula stuff, but that's okay. So 3x plus 1 equals x squared plus 7x minus 1. So basically, guys, we're going to be graphing a y equals this and a y equals this on the calculator. And then we get to see the point of intersection. I don't know why we weren't allowed to use the zeros for example 4 in that feature, because that would have saved a lot of time. That would have gotten me the answers immediately, but we didn't. So y equals 3x plus 1. And then y equals x squared plus 7x minus 1. I think the point of these ones is we need to see sometimes they might not intersect. Oh, I gotta change the windows now because I screwed something up. In fact, I'm gonna do funky windows. Just forgive me. I know exactly what I'm doing with this. You can ignore it. Unless they intersect outside of this region. That would be a problem. It intersects outside the region. Okay, I gotta zoom it out. I would have had to zoom out anyway. So let's go negative 20 to 20. Let's go negative 40 to 40. I just gotta see where the values are. I guess that's all that matters. Whoops, not table, graph. Okay, so we can see those, right? So intersect. I have an intersect feature under calc. Calc. Where do they intersect? First curve, sure. Second curve, sure. And let's see the right point where it intersects, right there. At x equals 0.4494, etc. They say round to the nearest hundredth. That's 2 decimal places. So one of these is x is 0.45. The other one with the intersect feature, first curve, second curve, guess, let's get closer to over here so it tells us which one we're trying to find. Negative 4.45. And there we go. That is those two. So, okay, I'm just going to go ahead and go about it like that. All right, these problems can go quickly if I work them out properly. Number 40. Negative x squared plus 2x equals negative 2x plus 5. I was trying to see if it's factorable. It's not. Sorry, I was going to say I can tell you these answers already. Okay, graphing calculator. Let's go. We're going to graph y equals negative x squared plus 2x. We're going to graph y equals negative 2x plus 5. I didn't put an x here. That would have totally changed the problem. And negative 2x plus... I hate doing this on... You know what else would be faster is if I had an actual calculator to show with instead of clicking on it. What am I going to do? I'm going to graph them and find where they intersect. Looks like they may only intersect once. In fact, I'm going to go and zoom on that one to be sure. But I'm guessing this is one of those where, they only hit once. Oh! Better yet. You can see there. There's the curve. There's the line. They don't intersect at all. If I try to hit the intersect feature, it would probably say error or something like that. No real solutions to this one. I didn't actually expect that. No real solutions. Definitely not factorable then, right? Discriminant, negative. All right, number 41. Got x squared minus 6x plus 4 equals negative x squared minus 2x. 2x. Okay, let's go ahead and graph those ones, shall we? And I'm going to have to reset this window. How do I, is there a way to, let's do z square. Does that, yeah. That's still the old one. I'll just change it back to these. Let's hope it's within the window range. Probably not. But at least here, I'm going to zoom in and out from this set. That's all I know. All right. X squared minus 6x plus 4. And then y equals negative x squared minus 2x. Negative x squared minus 2x. Okay, let's see these. They also don't intersect, and they're both parabolas. No real solutions here either. Clear as day, we can see that. I'm not going to try and do more with that one. All right, number 42. Sorry. All right, 42. 2x squared plus 8x plus 10 equals negative x squared minus 2x plus 5. This one I probably need to zoom out more for, just when I look at the left side. 2x squared plus 8x plus 10. And negative x squared minus 2x plus 5. All right, let's first see from here. Oh, no, it seems to kind of hit them. Cool. All right, so then they do intersect. They intersect twice. So intersect. Let's see this top one. Negative 0.61. Negative 0.61. You don't have to see what I'm writing yet. You just have to hear what I said. And then the other one, option 5. Let's get closer to the other one there. Negative 2.72. Okay. There we go. All right, 43. Now, see, I'm not really teaching anything right now. That's a, solution. It's clearly now just a solution guide. It's just an answer key at this point for these ones. Negative 4 times 1/2 to the x power. I will teach and state that once again, you can't multiply the negative 4 with 1/2 because it is, exponential order of operations. Okay, let's go negative 4 times 1/2, 4.5, whatever, to the x power. And then negative x squared minus 5. Negative x squared minus 5. All right, let's see if this decay fits all my stuff. Oh, that one's low. Did you see where that one went? Maybe it only hits once. This will be interesting. I'm going to zoom in down here. Let's see what it's showing. Here's the exponential curve. It might only hit once, and I'm going to say that because a parabola is not going to be as sharp as an exponential function. So my guess is this is the only point of intersection. I'm sorry if it's wrong. That's going off my own understanding of exponential functions versus whatever. So that intersection is negative 0.36. Negative 0.36 when you round. So just one answer to that one as far as where those intersect. And remember, an exponential function, it doesn't come back down. It'll just kind of flatten itself out there. So nothing's going to happen on the other side of that either. So negative 0.36. Still got 3 more of these. Now these are ones down below that I wouldn't solve algebraically with that quadratic formula stuff. I'd have to kind of refer more to what I'm doing right now or use that silly approximating method from before, which ain't gonna happen. All right, number 44. Y equals 1.5 times 2 to the x power raised to the x power minus 3. And then y equals negative x squared plus 4x. Oh, I'm at a wrong zoom. There's got to be a standard. Is that it? Okay, that's fine. There's an exponential, and here's a parabola. All right, it's going to hit twice. Okay, let's take a look. So we got 1 pretty close to 0, negative 0.43. And then the other one First curve, second curve. Let's guess it around like 4-ish. Oh, not toward 4, but that one. 2.21. Okay. All right. So there's that one. We got 2 more on this set. Number 45. I'm sniffing closer to the finish line by doing this. Number 45. 8 to the x minus 2 plus 3 equals 2 times 3 halves to the x power. So 2 exponential functions. I only expect these to intersect once. That doesn't mean they don't have to. They could intersect not at all. It's rare to see these ones intersect twice, but it's possible. You could make them intersect twice. I'm just expecting one intersection, and hopefully we'll see it straight up. Now, when you do 8 to this power, I'm going to use parentheses here for the x minus 2. Otherwise, that minus 2 won't be a part of the exponent. And then there's plus 3. And then over here, it says 2 to the 3 halves. 2 times 3 halves to the x power. All right, let's see from the standard if we hit this, right? Going to shoot up, and the other one's going to decay. Oh, if it decays, then it... Oh, it won't decay. Oh, this might hit twice. This might hit once, but I'm sure it's more of a hit twice thing. Let's see. Let's zoom in right here and see what's going on. So I guess I shouldn't question what they're doing when they're making problems for these. If they want it to hit twice, they'll have it hit twice. Here's the first graph. It hits twice. There it is. So it's possible to have it hit twice. Here's an example. All right. So let's go ahead and do that. So the first point of intersection we're going to see looks like the one on the left. 1.13. Okay. And then the one on the right, let's bring it up here. Come on, keep going. I just need to get it closer than the other one. Otherwise, it'll find the other one. It's doing a lot of processing, a lot of computing for these ones. Through 2.398, so 2.40. Okay. Oh, I'm sorry. You saw nothing that I just did. Okay. I'm going to show you the calculator. I'm not gonna edit more things than I need to. So let me go back and say what I did, show what it looked like. I apologize for that. I don't know how many people are watching this part anyway. That's what's troublesome with these things. I never sometimes see what I'm looking at. I've made bigger, dumber mistakes than that, though. Okay. Here's what the 2 curves looked like. And then I did a zoom in. I did a zoom in to here. I'm so sorry about that. Maybe you were watching this guy on TV. And I zoomed in and you saw this. I lay back and watch it. So I intersected twice, right? So we saw, I just wrote with 2 points of intersection more from that. So apologies on that. Hopefully you fast forward and you said, what is he doing? What are you doing? How do I do this? Hopefully after 1, 2, 3, 4, 5, 6 of those problems, that the 7th problem, it even made sense what I was going to do. All right, last one, number 46. These aren't perfect. Apologies to that. But as far as editing goes, it's not the editing that's the problem for videos, guys. It's rendering and encoding and stuff. And if I do all of that, it's going to take another set of hours to maintain the same quality for this amount of work. All right, let's go straight to the graphing calculator. Say, don't forget. I hope that wasn't the only problem I did that for. I hope that was the only problem I did that for, I should say. So negative 0.5 times 4 to the x power is the first equation. And then the next equation is 5 to the x power minus 6. So I should fully expect that they're going to have these things, intersect at more than one place again, or not at all. We'll see. Okay, just once. Let's see where that's hitting. Oh, I wrote 5x minus 6. 5 to the x minus 6. Let's do that again. This probably will only hit once, though, because one's positive, one's negative. So, okay, it still does, just by happenstance. So, intersect 0.90. Rounded. 0.90. Okay. Okay, guys. Enough fooling around with those. Let's see what else we have in store. Solve the system in exercise 37 using substitution. Compare the exact solutions to the approximated solutions. I'd rather do that. All right, so number 47, we take number 37, and they say solve using substitution, which is interesting because I actually used elimination to get the x's by themselves at the time. Okay, so we got 2x squared plus 6x minus 3 equals negative x squared minus x plus 5. I'm going to add x squared over, add x over, and subtract 5 over. Maybe this looks familiar now. Equals 0. Now let's solve using a method of choice. Quadratic formula seems most apt, especially since we know it's not factorable. So discriminant is b squared minus 4ac, which is 49 plus 12 times 8 is 96, which is 145, I think. 145 cannot simplify to my knowledge. 5 times 29, no. So we're going to leave it like that. Either way, we're going to use the calculator, right? So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, 2 times 3 being 6. So let's use these. We're going to do negative 7 plus this, negative 7 minus this. I guess we still got to use the calculator. But let's check those ones out. And then we'll compare them to the answers from before. They should be the same. I mean, this one will have more exact because we don't have to do any rounding. But we're going to do negative 7 plus root 145 divided by 6. I'm going to write it to 3 decimal places. So 0.840. And then let's do negative 7 minus that as well. Recall that answer. Subtract instead. And negative 3.174. Okay, so those are the 2 answers that I just got. Remember those, 0.840, negative 3.174. Let's go to my number 37. Oh, I was like 36. That's a way I got 3 answers. What happened? Negative 3.174 and 0.840. So they're the same when it comes to rounding, right? So when they said, what did they ask me to do for this? They said, compare the exact solutions. Oh, the exacts to the approximated. Oh, okay. Well, here are the exacts, right? Here are the exacts. Here's the approximated. I mean, compare them. I mean, okay, well, here they are, right? There's one and there's the other. I just wanted to make sure I got the same answers there within, and I liked that a lot more than what we were doing at the time. So there it is. All right, number 48. Compare, well, here's another one. Solve the system using elimination. Compare the exact to the approximated. It's okay, it's more of the same. But let's look at what those problems were. It said 38, right? Y equals, let's just write this down. Y equals 2x squared plus x minus 8. I think I did use elimination at the time to get it to that stage. So we will. Let's just make sure we said 38 was the question. Yep. So let's use elimination there as we did before. Subtract, we get 0. We get 1x squared. We get a plus x and minus 3. Negative 8 minus negative 5. So I think this is the one where I said, oh, let's solve using another method. Well, now's that time. Discriminant, b squared minus 4ac is 1 plus 12, which is 13. So your quadratic formula here, x equals negative b, negative 1, plus or minus root 13, all over 2a. There's 2. So there's the exact, the approximated. Let's go and go to the calculator, just make sure we got the same answers and, you know, all that stuff. But, I mean, that was a lot faster, right? So negative 1 plus root 13 divided by 2. 1.303. That actually sounds familiar. What was the other one? Negative. I can't remember. Negative something. It was a 303 thing, right? Negative 0.2, negative 2.303. So those numbers sound familiar. At least the 303 did. Let's make sure that I got those answers before for 38. Negative 2.303, 1.303. Okay, so they're the same as what I just wrote here. So, yeah. All right, they're compared. There it is. All right, number 49. Modeling with mathematics. The attendances Y for two movies can be modeled by the following equations, where X is the number of days since the movie opened. Oh, the attendances. Okay. One of them is for Five Nights at Freddy's. The other is for The Marvels. And they're both just declining in nature. I want to see one that goes up. I want to see where Oppenheimer sits. Oppenheimer didn't go up. That and Barbie did very well for themselves. What are we doing? When is the attendance for each movie the same? So we're solving for what value of X after how many days do they have the same Y. Notice they did not ask, oh, this is movie A and movie B. They did not ask what would that attendance be. To figure out what that attendance would be, you would substitute that number for X. This is just, yeah, that's attendances themselves. So anyway, yeah, let's go and solve. So I'm going to go for substitution. Negative X squared plus, I'm like, so I'm going to go ahead and approximate with the calculator. We might have to do a form of that. I don't know that these are rational. Let's add X squared over. So X squared, subtract 35X over, minus 40X, and subtract 100 over. Yeah, I don't know if this is rational or not. I'm going to have to do some work. Actually, I think it's 35 times 5. 35 times 5. So X minus 5 times X minus 35, I think is the factorization of that. So X equals 5 and X equals 35. So there were two different instances where this first one is an upside down parabola. So the attendance actually went up and then went back down, which is interesting. So after 5 days and 35 days, the attendance was the same. And the other one just had the attendance go down in general. Was the same. Now, because we can look at y-intercepts, for this movie, movie B, the initial attendance was 275 people. For movie A, the initial attendance was 100 people. And then that attendance went up after that, I imagine. The attendance went up after that to something. I'm not getting the vertex. It was after 17-something days. No, after 8-something days. So on the incline, it matched up with it, and on the decline, it rapidly went sharp down. This doesn't probably make sense in the real world for a movie model, but it's the problem, and they're having fun with it. So there you go. All right, that's number 49. Number 50. You and a friend are driving boats on the same lake. Your path can be modeled by the equation y equals negative 4x squared. Your path can be modeled by this. So 50. So this is you. Y equals negative x squared minus 4x minus 1. Your friend's path can be modeled by, your friend is so linear, y equals 2x plus 8. I'm sniffing using elimination, so 2x plus 8. Generally, I'm not an elimination hound. I generally don't look to use that method as a thing, but it's here. Kind of makes sense. I'm not saying it's bad. I'm just saying I generally don't do it. Do your paths cross each other? If so, what are the coordinates of the points where the paths meet? So we're solving for x and y if they happen. Probably makes sense to have them happen. And if they don't, then they don't. Minus 2x. Negative 1 minus 8. Oh, they totally cross paths. You know where? X plus 3 quantity squared equals 0. Perfect square trinomial that factors down. X equals negative 3. We cross paths once at negative 3. What's this whole thing about? You're driving boats and say your path can be modeled. What do x and y represent? I mean, they're just saying what are the coordinate points where we meet. We meet at negative 3 comma something. So what's the y value? 2 times negative 3 plus 8. Negative 6 plus 8 is 2. So they meet at negative 3 comma 2. So first of all, yes, we cross paths. And then where? At negative 3 comma 2. Just 1 point. We say hi and then bye and we leave. I mean, for a word problem, they just say, solve without. They just say solve. The arch of the bridge can be modeled by this guy. Kind of crazy. Where x is the distance from the left pylons. Boom. And y is the height in meters of the arch above the water. So, okay, that's where the arch starts. The bridge is up above at y equals 52. The road can be modeled by y equals 52. So y equals 52. To the nearest meter, how far from the left pylons are the 2 points where the road intersects the arch of the bridge? So we got to find this point and this point. Now, in a 2 scale, or with their units, we can see one's going to be a little more than 50, somewhere close to 50 or 60-ish. The other one's somewhere close to like 475 or whatever. So there's an inkling of what we're going to have. Maybe they're exact numbers. I have no idea. And they're not giving us a version of how we should solve this thing. I'm keen on using quadratic formula things. Now, if I do, I'm going to add this over. Minus 1.06x and then plus 52 equals 0. I'm also one of those ones where I like whole numbers only, sort of. So if I multiply this by, I think 500, 0.002, let's see, 0.002 times 500, I should get 1. Yeah. So I'm going to multiply that by 500, 1.06 times 500, and then 52 times 500. For some reason, I'm just big on just having whole numbers. So my equation is now going to look like x squared minus 530x plus 26,000 equals 0. I have no reason to believe this is factorable. It might be. I'm not going to bother with trying to figure out whether or not it is. So, you know what, though? I'm going to go for completing the square. X squared minus 530x, just because it's an even number now. Because I can. I'd prefer completing the square over a quadratic formula anytime that I have a 1x squared and even linear coefficient. Doesn't matter how big this is. I have a calculator for that. 530 divided by 2 is 265 and squared. 70225. And this is negative 26,000 plus 70225. I just like it more. This factors to x minus 265 squared. And this is that minus 26,000. I mean, I'm going to tell you guys right now that quadratic formula would be bigger numbers than these. I mean, given how I went about doing this. Square root of both sides. I don't know if this is a perfect... This could be a perfect square. If it is, that means it's factorable. And if it's factorable, that means it wasn't factorable. Okay, so let's just say this straight up. X equals 265 plus or minus... I'm not going to bother trying to simplify parts that I could, because you absolutely could, right? A 25 can come out from that, at least. So square root of 4, 4, 2, 2, 5. So we do want to do the plus or minus portion of this thing, right? Because there are two different sets of pylons for these. So the 265 minus, it won't be a negative number. It'll be positive. So 265 minus it is the leftmost, excuse me, not pylons, the where the road meets the bridge arch. So the first one, when you do 265 minus it, it's around 54.7. Remember when I said it was between 50 and 60? Is this in feet? This is in meters. So it's about this many meters from the left pylon. And then the right pylon, 265 plus root 44225. Is around I said 475, so it's around. Did they say how many? Whatever. 475.3 meters. It says 297. I'm just gonna go ahead and do the nearest tenth. Okay. Oh, to the nearest meter. I didn't even see that. To the nearest meter, 55 meters. And then here we have 475. So, okay, I was on point with that. So 475 meters for number 51. Okay. Great. Let's go to 52. Making an argument. I love to do that. Your friend says a system of equations consisting of a linear equation and a quadratic equation can have 0, 1, 2, or infinitely many solutions. Is your friend correct? Explain. I mentioned this earlier, maybe in the notes section or like on the core vocabulary and core concept checked or whatever. Your friend's incorrect. 0, 1, or 2 solutions is correct. And in a system, I'm going to explain as I type, and in a system of linear equations or a system of quadratic equations or of any matching degree, an infinite solution set is possible if they are the exact same line or curve respectively. What I mean by that is in a system of linear equations, you could have 2 lines that are the exact same. In a system of quadratic equations, you could have 2 curves that are the exact same. 2 parabolas, right? However, a line can never be identical to a curve. Now, it's not everywhere. It can intersect at a couple times. It can look the same for a moment before it branches out. So you cannot have an infinite number of solutions in such a system. So that wouldn't be possible because a line and a curve cannot be the same. Obviously, I could have described it a lot less, but because I'm typing and saying it out loud, I want to give you a complete answer. All right, number 53. In 53 and 54, solve the system of equations by all 3 methods. Which method do you prefer? Not graphing. Explain your reasoning. So I'm more of a substitution guy. No particular reason. It's just kind of what it seems to stem off of. I generally don't see elimination as something where I have y's on one side of the equation. My students especially, not my current ones, but if I'm teaching my IM1 students about things with this, I mean, they'll cancel these things out and pretend like 0 doesn't exist. They'll pretend like the equal sign doesn't exist. There's no reason why they'd ever do elimination very fondly with that. Okay, let's do graphing. These values shouldn't be terrible, I don't think. So I think the scale should be fine. The top equation is the linear one. I'll make that one blue. So 4x plus 3 is going to look like this. Because they're saying solve using all 3 methods, I'm going to assume they connect at like good numbers, like integers. Perhaps a faulty assumption, but let's go and give it a shot. So here's your line. The green one, let's get it in vertex form. I'm going to use the complete in the square set. So y equals x squared plus 4x plus something minus 1 minus something. That's a 4 and a 4. So this would be y equals x plus 2. Let's do that again. X plus 2 quantity squared, then minus 5. So your vertex is at -2, -5. It's hitting there. The stretch factor is 1. 1, 1. 2, 4. 3, 9. 4, 16. Okay, so it does go a little bit off the graph, but it's going to hit here, I think at 11. So that should be fine. So it's the vertex of this guy, and then it hits up there. Okay, so that is -2, -5, the vertex, and I think 2 comma 11. I mean, I'll double check that by solving using the other 2 methods. Now, substitution, listen, substitution and elimination start differently, but they end the same. Once I get it set equal to 0, which is my intent for these things, let's do substitution next. Substitution. This was graphing, by the way. Graphing. Once I set it equal to 0, it's the same thing either way. So actually, before I even say substitution or whatever, well, yeah, excuse me, substitution. Once I get to that set equal to 0, I'm going to solve. I'm not going to write. I'm going to use the same answer. So this is where I get to say x squared plus 4x plus 1 equals 4x plus 3. And then I will subtract 4x over, and I will subtract 3 over. Maybe subtracting 3 over wasn't the way to go about it. Maybe once you recognize you solve using square roots or something, that'd be fine. But I'm there. Elimination method, y equals, to line them up, I'm going to put 4x plus 3 here, and x squared plus 4x plus 1 here. As far as subtraction goes, 0, negative x squared, 0, and positive 2. So when I add the x squared over, subtract the 2 over, I get that. Now, would I actually subtract the 2 over in general? Probably not. But now I'm going to add that 2 back over. X squared equals 2. Wait a minute. These are different answers. What did I do wrong? That's a minus 1. That's a minus 1. That's a minus 1. Let's do that again. I'm like, wait a minute. There was a graphing problem. Minus negative 1 is plus 4. So minus 4. Sorry about that, y'all. That's a minus 1. Okay. 4. Got it. You could have solved by factoring or square roots. Take the square root of both sides. You'll get x equals plus or minus 2. Now, those are the two answers we get out of that. Let's substitute 2 into either equation. I like the top one. Y equals 4 times 2 plus 3, which is 11. Y equals 4 times negative 2 plus 3, which is 1. No. Sorry. Oh, negative 8. Negative 8 plus 3 is negative 5. Negative 5. So your two answers, whether you substitution or elimination, we get to that same stage. We got 2 comma 11 and negative 2 comma negative 5. Okay. And I think those were the same answers as above. Okay, which one do I prefer? Now listen, the graphing one here wasn't bad. I mean, if you're good on stretch factor or completing square and stuff. That was the quickest one, I guess, sorta. Because the plugging in after, it takes a minute. Overall, in this problem notwithstanding, overall I prefer substitution. Graphing leads to more maintenance and trust in a problem that has valid, I'm just telling you, that has valid integer vertexes, fits within your window range, etc. Elimination has more things that can go wrong. Specifically on the subtraction front. That also has a little bit of maintenance as well, right? My first thing was I had to kind of line up these things. You don't have to, but you're going to combine like terms. But I subtracted, right? At 0 minus x squared. A lot of people will put x squared. They're just going to bring it down. Things are going to go wrong here. Now, I copied this problem wrong. That was my bad. But there is a substitution afterward. I'm good on that. It's all good. Overall, I'm a substitution guy, it seems. Elimination hasn't been bad. I'm fine with it. But there's that. That was 53. My answer is going to be the same for 53 and 54, by the way. I prefer substitution more. But I'll be honest, graphing was pretty good on that. The window range on that 2 comma 11 just fell out, but it wasn't bad. Y equals x squared minus 5 and y equals negative x plus 7. I forgot that we had 2 questions to do. So when I wrote which one do I prefer, I already gave you my answer. All right, let's look at this one. For graphing. These, I don't need to do a vertex form thing for that top one. In fact, let's do the top one first. Negative 5 is the vertex and y-intercept, and you got a stretch factor of 1. Once more, they're finally giving us good graphs and saying, hey guys, you do like graphing, right? It's okay. There's not much wrong with this, is there? And like, no, did you see the problem that you gave me on number 7 and 12? Like, forget you. For graphing, right? They're like, no, guys, look, it's fine. And honestly, if I did a timer, I'd probably solve this one faster by graphing than either other method. But let's take a look. Boom, point of intersection. And then negative 1 slope. Boom. Look, they're going at an 11 again. Once again, window range is all the rage when it comes to relying on the fact that you have a graph at 2 scale and all that stuff. And plus, as far as maintenance goes, yeah, you need graph paper. I mean, there's a lot of maintenance involved with that kind of thing. There's a lot of trust issues there. Negative 4 comma 11 and 3 comma 4 is what it looks like. That's what it looks like. So there's graphing. Let's do substitution. This time let's set the problems up correctly. So there was y equals x squared minus 5 and y equals negative x plus 7. So as far as substitution goes here, we're going to say x squared minus 5 equals negative x plus 7. Add x over, subtract 7 over, and this is factorable. This is x plus 4 times x minus 3. So x equals negative 4 and x equals positive 3. Let's substitute these into an equation. I like the bottom one. So y equals opposite of negative 4 plus 7. And listen, I do a lot of this one in my head, right? 4 plus 7 is 11. And y equals negative 3 plus 7, which is 4. So we get final answers of negative 4 comma 11 and 3 comma 4 like we had above. Now for elimination, I'm only going to go until I set it equal to 0 like this, which will kind of be a first step if I write this correctly. X squared minus 5 and y equals negative x plus 7. Y minus y is 0. This is, oh, by the way, elimination. Y minus y is 0. X squared minus nothing is x squared. 0 minus negative x is positive x. Kind of tough. Negative 5 minus 7 is negative 12. And you can see where we go from here to there, solving the rest of the way. I would do the same stuff after that. Substitution or elimination. So same-ish. You can see where more things can go wrong there. Graphing might have been faster. I don't know, but I feel pretty good on that. Okay, my response is the same when it comes to which I prefer. All right, 55. Sorry, I was looking at how much time I've recorded for. I don't know how much space I have. The function y equals negative x squared plus 65x plus 256 models the number y of subscribers to a website. What, they end up going down? Where x is the number of days since the website launched. The number of subscribers to a competitor's website can be modeled by a linear function. The websites have the same number of subscribers on days 1 and 34. So A, write a linear function that models the number of subscribers to the competitor's website. B, solve the system to verify the function from part A. Okay, so this is negative x squared. Okay, so we need to make an equation where we have days 1 and 34. So 1 comma 34 is a point of intersection. This is a solution. 1 comma 34. That means this other graph needs that kind of point. This is something more for the IM1 crowd if you're in a point slope form. Y minus y1 equals m times x minus x1. I can use that form of something instead of plugging in 1, getting 34 out. You can use this, and I can make up whatever I want right here. Let's make up, I don't know, 3. I don't care. So 3 can be my slope. So every day they get 3 more subscribers. But it crosses through 1 comma 34 this way. Now I can do this whole thing, right? I can distribute, and I can add 34 over. So y equals 3x plus 31. So this can be my other equation here. Okay, now that's my competitor's website. Oh, I'm sorry. I said this totally wrong. Let me scrap everything I just did. I thought it said after 1 day you have 34 subscribers. I'm sorry. It says days 1 and 34 as solutions. Let's do that again. The websites have the same number of subscribers on days 1 and 34. So we need x to be 31 and 34 as solutions to this thing. My bad. Write a linear function that models the number of subscribers to the competitor's website. Okay, so what do I need to do here? I need to make x equal 31 and 34, get the same y values out for the linear function. I need to make it so that when this factors, I don't know if this is right in what I'm going to do. I'm thinking out loud. I got to work backwards from this thing. So I need answers to be, I need solutions, not solution. I need solutions to be x equals 1. Let's write it like this. X equals 1 and x equals 34. So x minus 1 and x minus 34 need to be factors to this guy, right? It needs to look like this, or a y, let's just write it as y equals blah, blah, blah. So that's x squared minus 35x plus 34. So I need this thing when compared to the other equation that I have, some y equals mx plus b. some ghost equation. I need, when I set these things equal, negative x squared plus 65x plus 256 equals some mx plus b. If I add x squared over, if I subtract 65 over with this mx, I have some mx and minus 65x. And I have some 256, excuse me, I have some b and I have some minus 256. This needs to equal my x squared minus 35x plus 34. In other words, this m minus 65 needs to be equal to negative 35, and this b minus 256 needs to equal 34. So I need m minus 65 to equal negative 35. I need b minus 256 to equal 34. That makes sense in my head on how I want to do that. If I add 65 over, I get 30. That's a different slope. If I add 256 over, I get 290. And that's a different y-intercept. Okay, I was making up my own based off point slope form. My bad on that. So my equation needs to be y equals 30x plus 290. Okay, let's verify. Let's solve this system and verify. Now, everything I do is going to get me back down to this equation. I'll say that. So I worked backwards to work forward to work backwards. Or I worked backwards so that I could work forward again back into this. So let's just do it down here. So y equals, I had negative x squared plus 65x plus 256. I have y equals 30x plus 290. So check this out. Let's use elimination. If we subtract, we're going to say 0 is negative x squared plus 35x minus 34, or x squared minus 35x plus 34 equals 0. This factors to x minus 34 times x minus 1. Using zero product property, we can say x equals 34 or x equals 1. Okay. All right, that verifies it, because obviously I worked backwards to get there. That's the only way I can think about that. I can't think of other ways that I would actually want to do that problem. But it's weird that I have to verify something afterward because I come off of that. So sorry what I first talked about. I thought they were saying after one day you'd have 34 subscribers or something. That's where my mind went. All right, number 56. The diagram shows the graphs of two equations in a system that has one solution. I agree. How many solutions will the equation have when you change the linear equation to y equals c plus 2? So this is y equals c. If it was y equals c plus 2, it would shift up 2 more and go up here. Sorry, it's not a straight line. It would be a horizontal line, and it would hit twice. I'm glad they don't have to ask me to explain that. I've explained it to you. Hold on. Y equals, let's kind of graph this. I feel weird if it doesn't have the graphs. I just do. Here's 1. Here's y equals c. And here's red. Okay. All right, part A. Y equals c plus 2. It'll have 2 solutions, because it would be shifted up. Part B, y equals c minus 2. That would shift downward. Remember, this hits tangentially, so this would shift downward. C minus 2 would be like right here or whatever. 0 solutions. No real solutions. Glad they don't ask us to explain, but it's all about the shifts, upward, downward shifts. All right, number 57. A system of equations consists of a quadratic equation whose graph opens up and a quadratic equation whose graph opens down. Describe the possible numbers of solutions to the system. Sketch examples to justify your answer. Well, there are 3 different sets. There's a 0, 1, or 2. So you can have quadratic graph opens up. Describe the possible number of solutions. You can have 0, which would look like, say something like that. We actually saw one of those. We could have 1, we'd have basically, well, vertexes don't have to collide. It can be a bunch of different versions of it. I could have one that kind of looks like the last ones, only it just, we could have vertexes collide, but it could also be like a, I don't know, something like that. Let's just touch it even closer to make it really look like it. Like one, boom. Yeah. And then we could have two. I don't know what that equation would look like. Hopefully they don't say come up with equations. But two, totally. All right. There's number 57. Number 58. 5 more questions, I believe. Up to 62, right? 5 more questions. Who knows how long they'll take. They say, graph these in 9 different ways. The population of a country is 2 million people and increases by 3% each year. The country's food supply is sufficient to feed 3 million people and increases at a constant rate that feeds 0.25 million additional people each year. Part A, one of the countries first experienced a food shortage. Part B, the country doubles at a rate which food supply increases. Okay, I have to understand part B a little bit later. Okay, so part A, population of a country is 2 million people. So I'm going to do these numbers in terms of millions, just so you know. Y is the population in millions. X is going to be the number of years. You can do something where you have 2 million people to begin with, and increasing by 3% each year is multiplying by 1.03. No time to explain. Getting the banana. X is number of years. Y equals millions of people. Okay, so there's a model for the first set. The country's food supply is sufficient to feed 3 million people and increases at a constant, so 3 million people, and increases at a constant rate of 0.25 million additional people each year. So every year they get a few more, a little bit more food you can work off of to keep feeding people with. So these are our 2 equations. When will a country first experience a food shortage is asking, when will this side, where's the point of intersection? And after that, when do you start to see a food shortage? So let's set those equal to each other. 2 times 1.03 to the x equals 3 plus 0.25x. I'm not going to solve this algebraically. I'm going to let the calculator kind of, work some things out for me. So we're going to do, in the calculator, 2 times 1.03 to the x power. And over here, I'm going to do 3 plus I probably should have done slope-intercept form, but 3 plus 0.25 times x. I don't know how far I have to zoom out for this. One's exponential, but it's like a curve thing. So I don't know how good or bad it's going to look. Let me just sketch the graph and see what's going to happen. Oh, it's going to be later. So it's intersecting once, but this is before, domain is from year 0 onward. So I got to zoom out. I got to figure out where farther on the right that this is actually going to happen. But I might have to change scales as well. Oh yeah, shoot. Okay, so let's see. I don't know how far I have to zoom out. I think if I just keep hitting zoom out, we're going to see more of the effect because eventually, guys, this graph's going to curve more upward, being that the 1.03% isn't much of a curve, but you can see it starting to take off there. So now we're going to see, okay, see over there, it's going to have some point of intersection. That's one we want to find. So intersect, and let's guess around that area. And let's see what we're seeing for a point of intersection. X, how many years? 84.1. So X is about 84.1 for a point of intersection. There's a negative one that I'm ignoring, right? X is greater than or equal to 0. So 84.1. So greater than it by after 85 years. Well, after 84 years. After 85 years, the country will experience a food shortage. So I don't know if they want to say 84 or 85. This is part A, by the way. Food shortage. 84, 85-ish, 84.1. Part B, the country doubles the rate at which its food supply increases. Will food shortages still occur? Yes, they'll still occur at some point. So doubling the rate is now taking part B. It doubles the rate. It doesn't double how much they had to begin with. It started at 3 million. That's still 3 million. But doubling 0.25 is now going to be 0.5x. Yes, you can change it to feed 500 million people per year. Eventually, even if it's billions of years from now, eventually an exponential function will always keep up with a linear function. So first of all, yes, it will. When? Let's go ahead and change that. Let's go to the graphing calculator again, and let's change this to 0.5 instead of 0.25. Just erase that little 2. And let's see if even this graph is sufficient here. Probably is. So there's the first curve, which that sharpness just dominates. Look, it's still going to intersect somewhere, so that's the point. Eventually, it still intersects. When let's plug in 150 and see what goes on. 115.48, so x is about 115.48. So after 116 years, within the 116th year, got to start purging the people. You already know the drill. All right, number 59. Use the graphs of the linear and quadratic function. I will. Let me copy this over because it has equations and everything. Well, and an ordered pair and all that. It's to scale, man. Totally. You copied it on your own paper, but here I go. Find the coordinates of point A, find the coordinates of point B. Well, okay. I'll tell you what. Remember that method I was talking about before for like, I wonder if this will work. That might work here. Okay, so I have, I'll put it here. I have two equations. I have y equals negative x squared plus 6x plus 4. And I have to make another equation. Oh, let me put that in blue. And then I'll do another one in red here. Now, the one in red, here's the thing. I kind of like my idea of point slope form. Y minus, this isn't in full function yet, but y minus y1 equals m times x minus x1. Those definitely points that crosses through. I don't know what the m is yet. I do know that somewhere this line intersects. Oh, you know what? I don't need that much information. Let's backtrack one. I keep going to point slope form, and you know what? We don't need that much. Y equals mx plus b. I know what b is. B is 4. B is 4 because it intersects at point A. A is the y-intercept, and the y-intercept of this guy is 0, 4. This is 0, 4 for A. Okay. B, on the other hand, is determined by, well, that's 0, 4, right? Well, we already put that, 0, 4. So what's the slope from 0, 4 to 2, 6? This m is going to be y2 minus, well, you're going to rise and run. Rise from 4 to 6 is 2. Run from 0 to 2 is 2. Yeah, so your slope is 2 over 2, which is 1. So your equation is y equals 1x plus 4, or x plus 4. To find b, you got to solve this thing. Now, we already know one of the solutions. X equals 0 is one of the solutions. The other solution, if I set these equal, I was really looking at elimination method there for a second. Add x squared over, subtract 6x over, subtract 4 over, that cancels out. Factor, you know x equals 0 is one of them, and x equals 5 is the other. Now this is the one to look at. Let's substitute 5 into this equation, 5 plus 4, y will equal 9. So that ordered pair for b, A is 0, 4, B is 5, 9. Okay. Sorry, I keep wanting to go to point slope form. I keep saying, hey, I have a known point on my graph. The first time I didn't. This time I actually did. And I actually didn't need to. I had a y-intercept, so I was all good. All right, 3 more questions. Number 60. Is it possible for a system of two quadratic equations to have exactly three solutions? Four solutions. Explain your reasoning. No. Not quadratics. Not with the leading degree quadratic. No, it is not possible to have exactly three. All right, guys, I'm back. And as a heads up, let me go back to this problem. I started to talk through some things, and I found out that I was my recording stopped again. I have insufficient space on my drive, so I had to clear a lot more things out. I actually had to transfer my video files over to an external just to get this recording in for 3 more problems. Let's get them in. I got to find a way to, it'll obviously already happen once this is uploaded. Find a way to merge all these files. It's late. It's 12:15 a.m. I got to find a way to get these all in. So for those who are still sticking around, who are the troopers for these last problems, I was typing this out and speaking it out loud. Here was the question. I got a system of 2 quadratic equations, a parabola and another parabola, whatever. Is it possible for them to have exactly 3 or 4 solutions? No, you can only have 0, 1, or 2. You can have infinitely many if it's the same curve, but otherwise 2 unique curves can only intersect as many as 2 times. That's just the nature of parabolas, where they curve, how they increase, things like that. If they were different degrees, yeah, they could intersect 4 times for certain things or whatever, but not for 2 parabolas, not for 2 quadratics. Number 61, I didn't start doing yet. I was speaking through it, and I was going to go to my graphing calculator when I realized I was out of space. So 61, I just copied down the problem, and it said, solve the system of 3 equations. Now, a system of 3 equations solved means it's got to be the same x that makes the same y for all 3. So the only thing I said was, because there's an exponential one here, I'm going to go to the calculator and find if all of them intersect together. They must. They probably do. And what is that point of intersection? We won't solve algebraically with an exponential. That's just not in our cards, at least not for IM2. That's for sure. So let me go to the graphing calculator, and we should have plenty of space on the computer now, enough for 3+ hours of work. So 2x minus 8, x squared minus 4x minus 3, and negative 3 times 2 to the x power. Okay, so let's change the window range back to standard and see where we're going from there. Got a linear, got a quadratic, and intersects in more than one place there, but all these intersect just at one place together, and it looks like that one. If I were to guess, I don't know what that is. Maybe it's not integers. So where do all 3 curves intersect? I'm just going to find out where these 2 intersect. Okay, 1, negative 6. So that's the answer. And look, I'm not going to go any farther than that. As long as there was an exponential equation, I'm not owing them any other explanation as to what kind of thing that would be. All right, number 62, last question. So despite all the merging and explanation, we got there. Find the points of intersection of any, if any, of the line y equals negative x minus 1 and the circle x squared plus y squared equals 41. Okay. So I'm wondering if this one has merit to use algebra as opposed to the graphing calculator, right? I'll tell you what, these will have points of intersection. I don't know if you know anything about circle equations, but this is going to have a radius. It's going to be centered around the origin, and it's going to have a radius of a little more than 6, close, 6.5, 7. And this is going to have a curve, line that goes like that. It's going to intersect in 2 places. What are those places? They're probably not pretty numbers, but we'll figure them out. So here's what I'm going to do. I'm going to take the circle equation. I'm going to get y by itself. 41 minus x squared. Take the square root of both sides. You get y is plus or minus the square root of 41 minus x squared. Now, this reveals 2 different parts of this. Positive root 41 minus x squared is this part, the top half. Negative root 41 minus x squared is the bottom half. So as you can see, the top half will intersect once, the bottom half will intersect once, if my concept of how this graph will work is on point. No pun intended. So let's see when let's see when the square root of 41 minus x equals negative x minus 1. Well, and when negative does, we're going to have, minus x squared. When negative does, we're going to get the same result, because the first thing I'm going to do here is square both sides of this. If I square both sides of this right here, then I get 41 minus x squared equals, and this is a x squared. It's hard when they're negatives for me to think about what that is. X squared plus 2x plus 1 still? I think it's still x squared plus 2x plus 1. X squared plus 2x plus 1. I add the x squared over, and I get 2x squared plus 2x. Subtract 41 over, I get minus 40 equals 0. Divide everything by 2, I get x squared plus x minus 20 equals 0. Okay, so I have this equation here. What my 2x's are going to be is from this. It's not factorable. Oh, it is factorable. I take it back. So this is, oh, they're good numbers. This is x plus 5 times x minus 4 equals 0. So x either equals negative 5 or x equals 4. Interesting. Okay. Now the y values, on the other hand, can also be clean. Oh, very nice. They can be very clean. All right. So when I plug in negative 5 for x, I'll get y is opposite of negative 5 minus 1. 5 minus 1 is 4. And here, when you plug in, is it going to be negative 5? Yeah. When you plug in 4 for x, you'll get y equals negative 4 minus 1 is negative 5. Cool. Okay, I didn't expect that. So your answers are negative 5 comma 4 and 4 comma negative 5. So negative 5 comma 4 must be this guy, boom, and 4 comma negative 5 must be that guy. Yeah, so that ends up being it. Cool, that was the last question. All right, guys, that'll do it for this one. So hopefully I edit and get all my merging woes here. This is Mr. Robinson. Thank you so much for watching this 4.8 stuff. I might skip 4.9 temporarily and go to the Chapter 4 review and take a look at some of these there. Take a look at some of those. Meanwhile, I know I've skipped some videos along the way, depending on when you're watching this in sequence. Otherwise, at some point down the line, you'll see a 4.9 coming after that. But hopefully this made sense. Take care. I'll see you in the next one, whatever that is.